Hi guys, good evening. We are going to be doing a slightly more difficult paper today. Not exactly that difficult because we are going to be spending today doing the first half of ASRJC 2009 Prelim Paper 1. Um, I I want to try to see whether I can finish question number 1 all the way until question number 7 together with you guys this evening. And if that is possible, then that will leave us more time to do the second half of the paper during one of the other days this week. And I don't know, I find this ASRJC paper a little bit more difficult than the last few papers that we have done, at least comparing the first half of the papers, because one very common style of how schools has been setting prelim papers, especially for paper 1, is to simulate something that is a bit more similar to what you guys are going to be facing during your A levels, which means that the first portion of typical paper 1 will usually be easier, and then slowly it will become either more tedious or become more challenging. So we are looking at the first half of ASRJC 2019 prelim paper now. And for those of you who are who are joining us for the very first time, we will probably be live streaming twice this week. So today we'll be doing the first half, and then after that, subsequently we'll be doing the second half of this ASRJC paper. Really? I thought the first question is actually pretty okay. So I find that as compared to the last few papers, this paper is generally a little bit more tedious, but I don't find the first question that tiring. Maybe we should try together like as soon as possible, because if I were to be doing all the 7 questions this evening, then we should really we definitely should try to just start now. Okay, so hang on, let me try to set everything right. And okay, let's start. ASR Anderson Serangoon Junior College 2019 it is a 3-hour paper. We are going to try to do from question number 1 all the way until this question number 7. Okay, that is my aim. If we cannot finish until question number 7, at least let's try to do until question number 6. But that will leave us less time for the next session that we are going to be having, because the last few questions are really very, very long, especially like question number 10 and the very last question, this question. It will require some time to discuss. But anyway, let's take a look at question number 1. It is a integration question. Okay, let's take a look at this question together. Okay, we are supposed to show algebraically that this can be rewritten into this form where fx is a polynomial. This week I discovered that there are some of us who aren't super sure what is a polynomial. So just in case, since most of us are going to be going for the A levels this year, and I'm assuming that most of you are J2, so A levels this year, please take note of details that are like this. Polynomial, that means we are looking at expressions that are like, for example, if A0 is the coefficient, then if A1 is another coefficient, it will be A0 x to the power of 0, A1 x to the power of 1, then A2 x to the power of 2, all the way until, let's say, an x to the power of n all the way. Or maybe we will just stop here as a maybe the polynomial will just stop here, where n here, they are all integer values, but not all integer values. It is going to be positive integers including 0. So this polynomial, which means that we are expecting fx to be a form that is something that is like this. Let me start. So we will have a square root of 1 minus 2x divided by 1 plus 2x. This is part A of the question. So looking at the denominator, the expression that we are supposed to show, I can tell that we are going to try to rationalize the denominator by multiplying the denominator here by its conjugate. So I'm going to multiply this expression by 1 minus 2x. So square root of 1 minus 2x over 1 minus 2x. So in the numerator, we will have a 1 minus 2x. And as for the denominator, it is going to be square root of 1 minus, okay, let me just write 1 minus 2x squared. This will give us a 1 minus 2x over square root of 1 minus 4x squared, which is what the question wants us to show. And we can see that fx is going to be a polynomial, a linear polynomial, 1 minus 2x. And making use of this, we are supposed to hence integrate this. So we are supposed to integrate the square root of 1 minus 2x divided by 1 plus 2x dx. And this is going to be integration of 1 minus 2x divided by the square root of 1 minus 4x squared dx. We do need some experience in integrating this. We will need experience, we will need standard formulas, some formulas we can probably get from our formula sheet, the MF26 that is going to be used in Singapore's A-level. So I'm going to try to break this up into two parts. One will be this over square root of 1 minus 4x squared dx. Then minus, minus 2 is a constant, so I'm going to take it out of the integration notation. And we will have this as x over the square root of 1 minus 4x squared dx. Okay. And for this first part here, there are two ways that we can integrate. We can either re-express 4x squared as 2x squared, or we can make use of what we have in our MF26, the formula sheet, which gives us a formula of integrating this a squared minus x squared dx. This is going to be equal to sine inverse of x over a plus c. This is given to us in our formula sheet MF26. I'm going to make use of this directly, which means that the coefficient of x has to be 1. So what I am going to do is I'm going to factorize out 4. So that will be 1 over square root of 4. Then we will have a square root of 1 over 4, which is 1 over 2 square. And this will be represented, where will be this a over here. Then minus away x squared dx minus 2. As for this, what I'm going to be doing is I'm going to be making use of the fx f prime x idea, where fx will be 1 minus 4x squared. Then f prime x, this will be minus 8x. So we need the minus 8x together with 1 minus 4x squared. And I don't think that is very difficult because we just need this extra coefficient of negative 8 here. So I am going to divide it by minus 8 so that I can introduce a negative 8x. So I can introduce a negative 8 into the numerator, and that will give me negative 8x. As for the denominator, I'm going to rewrite it as 1 minus 4x squared to the power of minus half dx. So 1 over square root of 4 is 1 over 2. And we will be integrating 1 over square root of half square minus x squared. If I were to make use of this formula, a is going to be replaced by half, which means that I will have a sine inverse of x over half. Then minus 2 divided by minus 8, this is plus 1/4. Integrating this, where I have my fx and this is my f prime x, this will be 1 minus 4x squared to the power of half divided by half, then plus c. So my final answer here is going to be equal to half sine inverse of 2x plus 1/4 divided by half. It is going to give me a 1 over 2. Then this will be square root of 1 minus 4x squared, then plus c. Okay, this will be part A. I think this is pretty okay. Furthermore, for integration techniques question, to prepare ourselves for integration technique, my personal opinion is it is the kind of topic that require us to just practice and practice and practice. The understanding of concepts for integration technique is actually of lower proportion as compared to the experience that you may gain through practicing for a topic that is like this. So in case any one of you find this a little bit more challenging, or if you find yourself being a little bit more intimidated by integration technique, my suggestion is to practice and practice and practice and practice your technique. Okay, I am pretty sure I haven't tried it and was doing this paper. I haven't tried it and I was doing. Oh, okay. Well, I am assuming that you are one of my tuition student, because we are doing the AJC 2011, but I thought this week we are doing AJC 2010 paper. So anyway, oh okay, 2010. This paper is a bit more difficult than the previous few papers that we have been doing on the live stream, but the second half can be a little bit challenging as compared to the first half of this paper. So and next, let's take a look at B. B can be tricky to some of us. So let's make sure that we see what we have in part B as clearly as possible. We are supposed to integrate. Let me make this a little bit bigger. We are supposed to integrate this. We are supposed to integrate from E all the way until E square of 1 over x and ln x. We are supposed to show that the result of this is ln 2. And what I am going to do is to try to make use of fx, f prime x again. If we were to see fx as ln x, this, and f prime x will be 1 over x, which means that if I can just re-express this, this will be something that is like this: e to the power of e square, 1 over x, which is this f prime x, is going to be here. Then fx is the denominator, so I have a 1 over, this is my fx, ln x, then dx. Okay. Sorry, I was looking at Claire's comment that this is a giveaway question. This paper is definitely harder than the A-levels. So I don't think this is a A-level standard kind of paper. Yeah, but A-level has been getting more and more difficult for us in Singapore. So practicing a paper that is like this is definitely very, very crucial, so that we can be our competency is higher than what we are supposed to be facing during the A-level. So anyway, this is my fx, this is f prime x. So it is as if we are integrating something that is like 1 over x. Integrating 1 over x is ln x. So this is going to be ln of modulus of fx, which is ln x. And from e all the way until e square. So this will be ln modulus of ln e square minus ln modulus of ln e. So this will be ln e to squares 2. I can bring it forward, so it will be 2 ln e. Ln e is 1. So this minus away ln e, which is 1. Ln 1 is 0. So here we have ln 2, which is what the question wants us to show. Okay, this is question number 1, part B. I actually have to agree that for certain questions that you guys are probably going to be facing during the A-level, it is going to be way more creative and novel. So okay. Okay, let me very quickly answer this question, okay, because I do think that it is possible for some of us to get a bit confused by how the integration here works. So for this, right, let me give you an example of how I got from here to here, okay? For example, if we have something that is like this, if we were to be integrating, let's say 2x of 1 over, let's say, x squared minus 1 dx. If we were to be integrating this, that means we will be taking fx to be equal to x squared minus 1. We'll be taking f prime x as 2x. So we have a f prime x here. This is going to be my fx. How do we integrate this? This is going to be ln of modulus of x squared minus 1, then plus c. So I'm trying to apply it here. So fx, f prime x, f prime x. So when I integrate this, I have ln of fx. So I have ln of fx, which is this ln x. But visually, it can be a bit distracting. But that is why I do feel that although I agree with what Claire says that this is sort of like a giveaway, but at the same time, visually it can be potentially a bit more confusing. Okay, so I'm trying to answer this. Why is it that 1 over ln x become modulus of become ln modulus of x? Okay, let me continue. Question number 2. I'm going to really try to finish all the first 7 questions today. Some of the questions in this first part are actually a little bit more difficult, or I would rather say that they are tedious. So it is not like they are going to be very easily overcome during the exam. For a 3-hour paper, I think the first part is actually very difficult to accomplish for a 3-hour time spent on the entire paper. So anyway, here we have this. We have a tangent of half y. This is equal to square root of 2x, where y is this. And I want to show this. So part 1, we are supposed to show this, and I think I'm going to just differentiate this directly. On the left hand side, when I differentiate this, we are going to be making use of implicit differentiation. So it is going to be secant square of half y. Then differentiating half y, this gives us a half dy dx. And this is going to be equal to square root of 2. And looking at what I'm supposed to show, it is 2 square root of 2 on the right hand side. So half, I'm going to bring it over to the right hand side. This will give me 2 square root of 2. So I will be left with a secant square of half y multiplied by dy dx. There's a dy dx here, so very likely this is going to be converted to 1 plus 2x squared. And I'm going to make use of trigonometric identity. The identity will be 1 plus tangent square a. This is equal to secant square a. So which means that secant square half y can be re-expressed as 1 plus tangent square of half y. So it will be this dy dx. This is equal to 2 square root of 2. And tangent half y is square root of 2x. So I can replace this by 1 plus square root of 2x square. Then dy dx. This is equal to 2 square root of 2. So now we have shown that 1 plus 2x square multiplied by dy dx. This is equal to 2 square root of 2. Yep, I agree with you, Claire, that the first question, right? Yeah, I feel that first question is a giveaway, but definitely not the whole paper, especially if we were to do a few more questions. Even in the first 7 questions, it is already going to be quite challenging. And I think the way this paper is set is sort of like different from VJC 2019. In fact, I feel that it is harder to score in this paper as compared to VJC 2019. Okay, but anyway, let me continue. Part 2. Part 2, we are going to make use of this result. So we are going to be making use of this result to find the first 2 non-zero terms of the Maclaurins for y. The Maclaurins for y, tangent is equal to this. So let me write down what is y. Y is going to be equal to tangent I'm going to shift over, 2 I'm going to shift over, so it is going to be 2 tangent inverse of square root of 2x. So we are supposed to find the Maclaurin's series for this. Let me erase this first. So we have now with us in part 1 1 plus 2x squared dy dx. This is equal to 2 square root of 2. And we know for Maclaurin's, there's a formula inside our MF26, the formula sheet that we are using during our A-level. This will help us to re-express any function into an infinite polynomial that will look like f0 plus x times of f prime 0 plus x squared over 2 factorial of f prime prime 0 and plus, let me just write down one more term, x to the power 3 divided by 3 factorial, f prime 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 0, and so on. So we would like to find all the coefficients, at least part of the coefficients, by continuously differentiating y. And one of the differentiation we have already gotten, which is in terms of, which consists of dy dx. We want to look for the first two non-zero terms. So my suggestion is, let's try to find out about the coefficient as we differentiate, so that we know exactly how many more times we are supposed to differentiate and when we are supposed to stop. So before I continue, let's check whether we have already gotten any, whether we have gotten enough of two non-zero terms. So let's check the very first one. When x is equal to 0, let's check y. Y here is going to be 2 tangent inverse 0, which is going to be 0. This gives us our f0. So this is a 0 term. Nope, we will have to continue with f prime x. So hopefully this will be our first non-zero term. F prime x, I'm going to be obtaining it from dy dx. So for dy dx, this is going to be equal to 2 square root of 2 divided by this, which is 1 plus 2x squared. X is going to be equal to 0, so this is 2 square root of 2. Okay, this is going to give us our first non-zero term. We need more terms to get two non-zero terms. So let's try to find f prime prime 0 by differentiating this one more time. So differentiating this, product rule, 1 plus 2x squared, then d square y dx squared, plus 4x of dy dx. This is equal to 0. Let's check whether this is going to be our second non-zero term. So I'm going to do that check again. When x is equal to 0, when x is equal to 0, d square y dx squared. This is going to be equal to minus 4x. X is going to be 0, so the entire expression is going to be 0 divided by 1 plus 2x, where x is equal to 0. So this is equal to 0, and this gives us our f prime prime 0, which is 0. Sorry, this gives us our f prime 0. So we are still not getting our second non-zero term, which means that we got to continue with our differentiation to get d cube y dx cube, and hopefully from there we will be able to find our second non-zero term. So let's differentiate this one more time. So I have a 1 plus 2x squared of d cube y dx cube. Then plus differentiating this, we have a 4x, then d squared y dx squared. Differentiating this, we have another 4x of d squared y dx squared. And by product rule, I'm going to differentiate 4x, which is going to give me a 4. Then dy dx. This is equal to 0. And I'm going to check for f prime 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 0. So when x is equal to 0, let me find out what is d cube y dx cube. And this is going to be shifting this over. We will have 0, 0. And this is going to be 4 times of dy dx. Sorry, negative 4 times of dy dx, which is 2 square root of 2. Then divided by this, 1 plus 2 times of 0 is this. So we have a negative 8 square root of 2. This gives us our f prime 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 0. So now we have another non-zero term, which is this. So now we will be able to form the Maclaurin's series that can answer part 2 of the question, which means that y, which is this 2 tangent inverse square root of x. This, okay, let me just write y, which is this 2 tangent inverse square root of 2x. This is going to be equal to f0. f0 is 0. Then plus x times of f prime 0. f prime 0 is 2 square root of 2. Then plus x squared divided by 2 factorial of f prime prime 0, which is 0. Plus x to the power of 3 divided by 3 factorial of f prime prime 0, and that is minus 8 square root of 2, and that is all I need to write because I have my first 2 non-zero terms according to what the question says. So y is going to be equal to 2 square root of 2x, then minus 4 square root of 2 over 3, x to the power of 3 plus dot dot dot. Okay. Okay, this is going to be, this is part 2 of the question. Let me move on to part 3 of the question. In part 3, we are definitely going to be making use of part 2 because the numerator 2 tangent inverse square root of 2x, this is going to be re-expressed as this. And we are supposed to re-express this in ascending powers all the way until x to the power of 3. And this has x to the power of 3. So I'm going to be making use of this to replace the numerator. As for the denominator, we have a cosine 2x. And I'm going to make use of our MF26, the formula sheet. And in the formula sheet, we have a cosine x. And cosine x, according to the formula sheet, we can write cosine x using our MF26 as 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial and all the way until infinity. I see somebody asking about the dot dot dot. I find that it's a bit interesting because on Saturday when we were doing, what is that paper that we were doing? We were doing oh no, what is that paper that we were doing? APGP paper 2. Somebody was also asking about the plus dot dot dot. I think if you were to write plus dot dot dot, then you will use an equal sign here. But if you decide not to put in a plus dot dot dot, I would suggest that you put in an approximation notation, then write this as square root of 2 square root of 2x, then minus 4 square root of 2 over 3, x to the power of 3. Okay, this is my suggestion. Yeah, APGC. So anyway, let me do the last part of this question. So from the previous part, this is what we have gotten, that this is equal to 2 square root of 2x minus 4 square root of 2 over 3, x to the power of 3, and so on. Or you can put an approximation notation so you can avoid the plus dot dot dot. We are going to be making use of this to work on part 3, and together with what we have in our MF26 to re-express cosine 2x. So let me rewrite the question first. We are supposed to re-express this square root of 2x divided by cosine 2x. So the numerator, I'm going to rewrite it as 2 square root of 2x minus 4 square root of 2 over 3 x to the power of 3 divided by cosine 2x. I'm going to be making use of this, but replacing all the x by 2x. You'll give me a 1 minus 2x squared over 2 factorial. The next term will be 2x to the power of 4. But since the question is asking us to expand all the way until x to the power of 3 only, I'm going to ignore the x to the power of 4 in this expansion here. So I'm going to ignore the rest of the terms. So we have this, which means that we are going to be getting a 2 square root of 2x minus 4 square root of 2 over 3 x to the power of 3. This divided by 1 minus this, which is going to be equal to 2x squared, and so on. And in order for me to continue rewrite this in as a series that is in ascending powers of x, I'm going to shift the denominator up and rewriting it as this 2 square root of 2x minus 4 square root of 2 over 3x to the power of 3. And I will have this as 1 minus 2x squared all the way until minus 1. And in order for me to re-express this into a polynomial, I'm going to be making use of another formula that is in the MF26, which is going to be 1 plus x to the power of n, specifically used for the kind that is like a binomial expansion. So I have this, then nx plus n minus 1 divided by 2 factorial x squared, and so on. So I'm going to re-express this as 2 square root of 2x minus 4 square root of 2 over 3x to the power of 3. I will re-express this as 1 plus minus 2x squared, and so on. So that I can re-express this as two terms. One term is 1, which is synchronized to this, and x is going to be replaced by minus 2x squared, and so on. So now we have this as 2 square root of 2x minus 4 square root of 2 over 3x to the power of 3. And as for this, I can re-express it as 1 plus n, which is minus 1, multiplied by x, which is going to be this second term here, minus 2x squared, and so on. As for the next term, I'm going to be getting an x squared, which means that it is going to be this square, which will give me a minimum of x to the power of 4 as the degree of whatever that I'm expanding. So I'm going to ignore the rest of the terms. So I will have a 2 square root of 2x minus 4 square root of 2 over 3x squared, and so on, multiply by 1 plus 2x squared, and so on. So this times this gives me a 2 square root of 2x. Then plus this times this gives me a 4 square root of 2x to the power of 3, which I'm still going to keep because I want all the x to the power of 3 terms. This times this gives me a minus 4 square root of 2 over 3x squared. And this times this I'm going to ignore. This times this I am, this to the power 3. So here is power 3. And this times this I'm going to ignore because it's going to be getting more than this x to the power of 3. So the rest of the terms I'm going to leave it as this dot dot dot. So evaluating this, we will have a 2 square root of 2x plus 8 square root of 2 over 3 x to the power of 3, and so on. Okay, I have to say, right, this question isn't supposed to be that long. It's just that I'm writing down all the details. If I skip some of the details, it can actually be done a little bit faster. But one thing that I realized that is sort of like a little bit more of a characteristic of the first half of this ASRJC paper is that it's very tedious. Even the substitution that we are going to be seeing in the next few questions, they are all going to be a little bit more tedious than usual. That is why if you are practicing this paper without looking at the time, I think it may still feel pretty okay. But I can imagine for an ASRJC student doing this paper last year, it's definitely going to be quite challenging, because probably even the first half, let's say question number 1 to question number 7, will probably take up I don't know, I wonder if some students will be spending like almost 2 hours on the first 7 questions of this paper, okay, because of how tedious it is going to be. Let's take a look at question number 3. Okay, hi. Next, question number 3. This is a vectors question. Okay, I guess we should try to draw a diagram for this. The position vectors of A, B, C are this. So we have OA is this, we have OB as this, and we have OC as this. N is lying on AB such that A and B, the proportion is 2:1. O is the midpoint of CN. Okay, C is, let's say, if C is, let's say, somewhere here, then O, the origin is going to be the midpoint. I want to prove this. Let me draw a proper diagram to see whether we can take a better look at what that is described to us so far. So we have something that is like this. Let's say this point is A. Let's say here is B. I am going to try to reference this to the origin. Let's say the origin is here. So we have this. For example, this is O. So N is somewhere that is here. And the proportion that we are talking about is 2:1. And C and O is the midpoint of CN. So we probably will be looking at something that is like this. Let's say this point here is point C. So here is point D. The vectors that are given to us are OA, OB. So we have this, and OC, which is going to be this. And since O is the midpoint of CN, so this should be minus C, correct? Because if this is C, this is minus C. So I guess the first thing that we can try to do is to find ON using ratio theorem. So ON, this is going to be 1 time of A. So 1A plus 2 times of B. So I have this divided by 1 plus 2. So ON is going to be equal to 1/3 of A plus 2B. And ON is actually minus C. So I will rewrite this 1/3 of A plus 2B, which is ON. This is going to be negative of C, which means that A plus 2B, this is going to be minus 3C. If I were to bring everything over to the left hand side, we will be able to show what the question wants us to show. A plus 2B plus 3C is equal to a 0 vector. Well, let's be careful. I see a lot of students getting marks minus off for the presentation of this. I'm reminding myself too that when I try to add all the vectors together, I should be getting a vector. Even if it is a 0, it should be a 0 vector. Next. Okay, part 2. Question 3 is similar to a vector question in the O-level. Okay. I actually tried to do the O-level question. I tried to do the O-level paper from last year, but I can't really remember. I'm more of a like H2 math person. So anyway, okay, M is on CB such that CMMB is 2:3. We are supposed to prove that AOM, they are collinear. So let me erase this. I'm going to place B here. Okay, let me be a little bit more consistent. I'm going to use red color for my diagram. So I'm looking at this, and M is supposed to be somewhere here, such that CM is to MB is ratio of 2:3. And we are trying to check whether these AOM are collinear. So I guess to check that they are collinear, I will first try to find the position vector of M. And I'm going to make use of ratio theorem again. So it's going to be 2 times of B plus 3 times of C. This divided by 2 plus 3. So 2 plus 3, 5. So we have a 1/5 of 2B plus 3C. Looking at this, we can see that 3C is going to be equal to minus A minus 2B, correct? From here. Okay, 3C is equal to minus A minus 2B. So if I were to replace C here, if I were to replace this 3C here by minus A minus 2B, I will get this, which leaves me with B, and B will disappear, leaves me with a minus 1/5A. This tells me that OM is equal to minus -1/5 of -1/5 of OA. So OM and OA, they are parallel to each other, and this tells me that AOM, they are 3 points that are collinear. Okay. Okay. Then part 3. Okay, I'm seeing some of you are trying to discuss about being O-level. Okay, anyway. If the point P is such that NP is equal to AM. Okay, and we know AOM, it is going to be a straight line. So AM is going to be passing through O. And MP, a vector, is the same as the vector AM, which means that I'm looking at something that is like this, right? Something that is like this, where NP, this vector, should be the same as AM, this vector here. So we have this. Find the ratio of the area of PNAM. This should be a parallelogram, right? Because this vector is the same as this vector. So they are parallel and they are of the same length, which means that PNAM, this is going to be a parallelogram. And we are looking at the area of another shape, which is PNOM. This is parallel to this. So this other shape that we are looking at is a trapezium. Let me rewrite what we have here so far. Okay. From part 2, we have deduced that OM is equal to -1/5 of OA. Okay, this will be a useful piece of information. I'm going to make use of it in a little while. Let me erase this first. And okay, maybe I should just try to redraw the diagram so that we can, all of us can see a little bit clearer. So we have a parallelogram. So our parallelogram, let's say it is like this. A and PM. So PNAM, this is a parallelogram where this is going to be the same as this. And we are looking at a trapezium, which is something that is like this. The origin is here. And from this, we know that OM is 1/5 of OA. Or we can also see this as the length OM is 1/5 of the length OA. So OM over OA is going to be 1:5. So this proportion here is 1. This proportion here is going to be equal to 5. And the reason why I'm doing this is because to find the area of the parallelogram, it is going to be base times height. And for the trapezium, it is going to be half times height times sum of parallel sides. So the trapezium and this parallelogram, they are actually going to be sharing the same height. Let me draw the height for you to see. It will be, let's say from this point, I'm going to draw a line that is perpendicular to the base. So this is the height. I'm going to call this h, is the height of the parallelogram. I will also consider this as the height of the trapezium, which means that if I were to consider the area of the parallelogram PNAM, this is just base times height. So this multiplied by this, NP is the same as AM. So I'm going to just use AM as the base. So AM times H. I'll show you why I'm using AM, because of the area of the trapezium. Because now if I were to consider the area of the trapezium, PNOM, this will be half times height times sum of parallel sides, which will be NP, which is the same as AM. So it will be AM, NP, which I'm writing as AM because they are the same length, plus this, and this is 1/6 of AM, correct? This is 1 proportion, this is 5 proportion, so this is 1/6 of AM, which means that we will be getting a 7/6, then times 12, 7/6 times half, this will be 7/12 of AM multiplied by H. And this will give us the ratio. I'm going to write it in a form of fraction first. So the area of PNAM divided by the area of PNOM. This is going to be equal to AM times H divided by 7/12 of AM times H. So AM times H, AM times H can be cancelled. This is going to be equal to 12/7. So the ratio that we are talking about, which is the ratio of area of PNAM is to PNOM, is going to be 12/7, which is 12:7, which is what the question wants us to show. Yep, AO is to OM is 1:5. Okay, like what I wrote here, which we deduce from part 2. Okay, we know vector OM is -1/5 of OA. So the length OM should be 1/5 of the length of OA. Okay, this is question number 3. Yep, we have finished question number 3. Let's move on to question number 4. Hang on, let me see this question. 1 minus the area of 1 minus the area of AON divided by the area of PN04. So it will be PN, it will be PN, yep, okay. Okay, because if we are talking about the ratio of if we are talking about the ratio of a parallelogram divided by the ratio of the divided by the area of the trapezium, then area of parallelogram, so if we are talking about this, the area of the parallelogram divided by the area of the trapezium. Then this parallelogram is going to be the triangle. This triangle is what you have quoted as AON. AON plus the trapezium, then divided by the trapezium. So this will be AON divided by the trapezium plus 1. Oh, sorry, you are using another strategy. So your parallelogram, which means, right, Claire, that means you will be getting a 7/12, right? Okay, so for Claire, what you are saying is you're doing the reverse. The parallelogram minus away the triangle divided by the area of the parallelogram. So you'll be getting a 7/12 instead. Anyway, yep, it is okay. Let's take a look at question number 4. Yeah, I think it is actually possible for us to finish 7 questions. Let me just quickly move on first so that I can try to touch on all the 7 questions. It is going to get a little bit more tedious. Okay, question number 4 here. Question number 4, there are 2 parts of this question. We are supposed to, the first part, 4A, the first part is for us to be sketching f modulus of x, and that is extremely easy. I will still sketch this. Let me take a look at this. F modulus of x. So for f modulus of x, we are going to be retaining this portion here, and we'll be ignoring this part. And for whatever that is on this portion, we will be reflecting it about the y-axis. So let me try to replicate this first. So there is this horizontal asymptote, like what I've been telling you guys. I seriously find drawing asymptotes first a very, very good idea whenever you try to sketch a graph. So there's a horizontal asymptote, y is equal to 2. There's a vertical asymptote that is on the right hand side. I'm going to sketch that also. So we have this. This is x is equal to 2. This part of the graph is going to be retained. So we will draw it something that is like this. And I'll make sure that my graph tends towards the asymptotes as much as possible. So something that is like this. This point here is going to be 3. This point here is 4, 5. And we have this portion here, which I can't really remember. Did I remind you guys that when we are drawing this portion here, let's make sure that this is a sharp point with respect to the x-axis, because I do think that there will be some people who will draw this in this way. We're trying to make this part tangential to the x-axis, and if you were to look at the original graph, it is definitely cutting at an angle. So we must make sure that it cuts at an angle so that when it is being reflected, the vertical asymptote is going to be reflected. So let me draw in the vertical asymptote first. This will be x is equal to -2. When it is being reflected, this should still be a sharp point. So like this, all the way tending towards the asymptote. And we will have this tending from the asymptote up. Oh goodness. So we have this and tending towards the asymptote. This point here from 4, 5 being reflected about the y-axis will become -4, 5. And this point here will become -3. Okay, let's make sure that this particular intersection with the x-axis has to appear as a sharp point. Especially during the exams, I do see a lot of students losing mark because they were drawing it in this way, and that is why for a lot of markers they will try to watch out for mistakes that is like this as a presentation. So even if you didn't have the intention of drawing it as a as a, something that is like this. Even if you don't have intention of drawing it as this, please make sure that you exaggerate this a little bit, okay, to make sure that it looks like as much as possible to be like a sharp point. Next, let's sketch the graph of y is equal to f prime x, which I don't think it is a very unexpected or very challenging question also. So to sketch the graph of y is equal to f prime x, I highlighted a few steps that are on the Achevas TV outline. In the theory outline under differentiation is where I talk about the graph of y is equal to f prime x. I just realized that my head is my head is blocking this. But anyway, sketching the graph of y is equal to f prime x, I have a certain there are a few steps which I'm going to try to use them here. I think that will increase the consistency of us. That will increase the consistency of us getting marks in the exam. Oh, that day we were saying, right? Let me very quickly talk about this issue here, okay? When do we draw it as a sharp point? When do we draw it as a round point? So if you were to, first of all, what we are trying to do is to do a reflection of the geometry that we are seeing here, a reflection. So if you were to look at this point that is here, which is going to be reflected across to the other side, right? If you, here to me, it is coming at an angle, which means that if I were to try to, let me use another color. If I were to try to draw a tangent at this point here, a tangent will be at an angle, right? Which means that if I were to be reflecting this portion, if I were to be reflecting this portion of the graph, the tangent, the corresponding tangent will also be at an angle, which means that the reflected graph will be this way. So here it is going to be a sharp point. But if for the original graph, it happened to be like this, a turning point, for example. Well, let's say it happened to be a turning point. So I know for this part of the graph, the tangent is going to be parallel to the x-axis, which means that when I reflect this red colored portion about the y-axis, the tangent is still going to be parallel to the x-axis. So the reflected portion is going to give me 1, where it is going to be rounded. Okay? Okay, that is why for this particular question here, what we are seeing here is a sharp point. And okay, let me take a look at f prime x. The graph of y is equal to f prime x. One of the most crucial thing that I think we should do, although I have some steps that are on the theory outline on the Achevas TV, but the most important thing that we should take note of when we try to sketch the graph of y is equal to f prime x is that when we are sketching this graph, all the y coordinates that we are going to be seeing here are going to be the gradient, the value of the gradient that we are seeing over here. Okay, because just based on this understanding, you're actually able to draw very, very accurately the graph of y is equal to f prime x. Because for all of us, we should be able to understand and observe the value of the gradient. For example, the gradient that is here is going to be negative, but it is not. But as x increases, the gradient becomes more and more negative, which means that the y coordinate is going to become more and more negative, since the y coordinate represents the gradient that we are seeing on this graph. And a few steps that I try to take is on the Achevas TV theory outline is, number 1, I will try to ignore the x-axis. I was telling my students during the tuition that this is a little bit weird. I can understand why should we even ignore the x-axis, because I do realize that sometimes students get very confused about points where the curve cuts the x-axis, and they were trying to do some transformations to points that is like this, for example changing these points to vertical asymptotes, etc. But let's take note that what we are trying to watch out for are the gradients, which means that even if I were to translate this graph vertically up by maybe 5 units, the gradient at this point and the graph that is being translated up, they're going to still share the same gradient. So it doesn't really matter how or where the graph cuts the x-axis in this case. So the very first thing that I will suggest, it is not very crucial, is not to let the x-axis distract us. Number 2, we will take a look at all the asymptotes. The reason why we will look at asymptotes is because asymptotes here will affect the asymptotes here if there were to be any. And what we are trying to do is to sketch in all the asymptotes first. So why not, right? So if you were to look at the asymptotes, we have a horizontal asymptote, but we are looking at a gradient. And for this horizontal asymptote, the gradients at the two ends are 0, which means that we will have a y equal to 0 as the horizontal asymptote, since y represents the gradient that I see here. Next, we have a vertical asymptote. Vertical asymptote is the value of x, which causes fx to be undefined, which means that it is going to be the x where I will not be able to find any gradient, since there is not going to be any fx here, which means that the vertical asymptote will remain as the vertical asymptote. So I have it here. X is equal to 2. Then the third thing that I try to suggest, after we have worked on all the asymptotes, then I will try to, the third thing that I suggest is to look at all the easier points where we can read the gradients directly. For example, points where f prime x is equal to 0, like for example here. So when x is equal to 4, f prime x is equal to 0. So my graph should pass through the point 0, 4. When x is equal to 0, y, which is f prime 0, f prime 4, should give me a 0. So we have a 4, 0 here. F prime x. With that, this is the only point, so I guess this is it. And the fourth step that I was suggesting is to step back and try to just review your entire graph, asking yourself where are all the positive and where are all the negative gradients. So on this portion, all the gradients are negative, which means that the y-coordinate on the left-hand side of 0 will be negative. The y-coordinate between 0 to 2 will be negative. And as for 2 to 3, the y-coordinate is positive. 3 to 4, the y-coordinate, the gradient is going to be positive. So 2 to 4, 2 all the way until 4, the y-coordinate should be positive. Then after that, the gradients are going to be negative, which means that the y-coordinates are going to be negative. So I'm expecting my graph to be residing here, here, and then below the x-axis here. And the very last step, which is the most crucial step, it is the step that displays our understanding of the graph of y is equal to f prime x, is to just go from the left to the right, looking at the gradient, and then trying to sort of like plot it or sketch it on here, representing it as the y-coordinate. So all the way to the left, we can see a negative gradient, but a negative gradient that is actually still pretty close to 0. So the y-coordinate is going to be here. Then the gradient becomes more and more and more negative. The gradient of the tangent becomes more and more negative. So the y-coordinate will also become more and more negative as it tends towards x is equal to 2. So I have a graph that is like this. And it's synchronized to where I've ticked, because I'm expecting the y-coordinates to be negative since the gradient is negative. Then the gradients are all positive here. So from 2 onwards, the gradients are going to be here. But it is going to be a very, very positive gradient, then slowly goes to 0 gradient. So the y-coordinate will be super positive, then slowly goes to 0, which is a point that we are really expecting. At this maximum point, the gradient is 0. Then the gradient becomes more and more negative. So the y-coordinate will become more and more negative. And then it will become less and less negative, then going back to 0. So the y-coordinate will become less and less negative, going back to 0. But I will never know where exactly this happened, because the question didn't give me this set of information. So I'll just leave this as this. So this is my graph of y is equal to f prime x. I will suggest that we try to quote the asymptote, to label the asymptote y is equal to 0, because the question did mention that we are supposed to indicate clearly all the coordinates of the turning points, the x-intercept, the axial intercepts and the equation of the asymptotes. So for me, I do suggest that you indicate this. We're not leaving the examiner to guess whether this student, although it is pretty obvious, okay, but we don't have to risk by letting anyone even suspect that we didn't know the x-axis is the horizontal asymptote. So why not we just label y equal to, label this horizontal asymptote as y equal to 0. Okay, I think 4A is pretty okay. 4B, I have a strategy that I want to share. It is not a very common strategy to see being done in a school, but I believe that it is a very, very efficient strategy. And if you have never had any good way to deal with question that is like B, I would really suggest that you consider the strategy that I'm going to be talking about next. Because what a lot of people try to do for B, for something that is, for a question that is like this, is they try to do a reverse of all the transformations. And this kind of reversal during the exam can be a little bit more risky a bit because it requires a bit more processing. But let me show you a way that we can actually reduce the processing but increase the precision of how we are going to do question that is like this. The first thing that we should do, and we cannot avoid this, is still to try to understand and write the transformations that are given to us by the question in the form of notation. So we still need to understand the transformations. For example, if I were to start with fx, I know fx is going to be transformed by stretching it with a scale factor of 2 parallel to the x-axis. So if I were to scale this by a factor of 2 parallel to the x-axis, that means I'm going to be replacing all the x by half x. So the first transformation here, notation wise, is replacing x by half x, and I have this. Then it is going to be a translation of 2 units in the negative x direction. Translation of 2 units in the negative x direction means that we are going to be replacing x by x plus 2. So it is going to be a translation of 2 units in the negative x direction. So this will give us a f half x plus 1. And finally, the third transformation, it is a translation of 3 units in the positive y direction. So it is taking this half x plus 1, then plus 3. Translation of 3 units in the positive y direction. And according to the question, this final graph, half x plus 1 plus 3, is equal to this ln e to the power of 3x. So what some people tend to do is, probably most people should be able to do this. But what I suggest is, instead of trying to reverse the process of transformation and then translating it to algebraic to get your original expression, my suggestion is my suggestion is working on this, and we continue to transform forward. I'm not sure whether I am describing it like clear enough to you guys, but let me show you what I'm trying to say. Okay, so from here, my aim is to try to continue to transform this so that ultimately on the left hand side I get an fx. So for example, the first thing that I'm going to do is definitely shifting this 3 over to the other side. So I have a half x plus 1. This is equal to ln e to the power of 3x, then minus 3. In fact, we can simplify this a little bit. This will be e to the power of 3 plus ln x, then minus 3. Ln e to the power of 3 is 3. So 3 minus 3, this will leave me with a ln x, which means that I have a half f of half x plus 1 is equal to this. Then, algebraically, what I'm going to do is I'm going to replace x by, for example, 2x. So, I will replace x here by 2x, then plus 1, which means that this x, I will also replace it by 2x. I am continuing to transform forward. I'm not trying to reverse back the transformation process, which means that algebraically on the left hand side, notation wise, we will have a fx plus 1. This is equal to ln of 2x. And we will continue our replacement by replacing x by x minus 1. So I replace x by x minus 1, then I have a plus 1. This is going to be ln of 2, replacing x, all the x that I see, by minus 1. So on the left hand side, we have fx, and on the right hand side, it is going to be ln 2x minus 2. I find this very, very simple to replicate in the exam, and I find students who try to use the reversal of transformations to try to work backwards algebraically, facing problems sometimes, okay, during the exam, because you're rushing, and then at the same time you're trying to process the reverse of transformation, and every time when you try to reverse a process that you are more familiar with when you go forward, it is a challenge during the exam. That is why I suggest something that is like this. We cannot skip our ability and understanding of transformation, but after we have completed the transformation, we can actually use an algebraic process to reverse by continuing to transform forward. Okay, it's a very, very good strategy. Yeah, I can see some of you are understanding this strategy, so please continue to use this. Okay, it's very, very useful. Let me continue with the next one, question number 5. 5, and then I'll do 6. 6 is pretty fast. 7 is going to be very tedious. Let me see whether I can finish the next 2 questions a little bit faster. Wow, Jack Ng for president. Question 5 is not easy to do during the exam. It is not difficult, but there are too much details in 5. So I feel that is a very very challenging question for exam. Okay, we are given a parametric equation, and we know that t is going to be between 0 to pi over 2. A is a positive number, and part 1, I'm supposed to find the Cartesian equation. So to find the Cartesian equation, part 1, I have x, which is equal to a sine square t. And I'm going to try to make use of trigonometric identity. So sine square t, this is equal to x over a. And I have y to be equal to a cosine t, which means that cosine t is y over a also. And I'm going to be making use of trigonometric identity, sine square t plus cosine square t, this is equal to 1. So we have x over a plus y square over a square. This is going to be equal to 1. I can leave it as this for my Cartesian equation, or we can also try to multiply the entire equation by a square, which will give me an ax plus y square. This is equal to a square. Let me just write down my Cartesian equation here. So I have ax plus y square. This is equal to a square. And let's not forget about this, where we are supposed to state clearly any restrictions to the values of x and y. With this x here and this y here. So to discuss about this, I am going to be making use of the fact that t is supposed to be going from 0 to pi over 2. So when t is bigger or equal to 0, less than or equal to pi over 2. Looking at x, we can see that for sine t itself, sine t, it should be between 0 to 1, correct? Because I know that when I have t, if I were to say this is y, from 0 to pi over 2, sine is going to be like this. Of course, it will continue, as the sinusoidal graph, but from 0 all the way until pi over 2, it's going to be like this, and it's going to be 1. It is bigger or equal to 0, less than or equal to pi over 2. That is why sine t is between 0 to 1, and inclusive of 0, inclusive of 1, which means that sine square is also going to be between 0 to 1, and a of sine square t is going to be between 0 and a. And the reason why we can multiply this by a throughout is because the question actually gave us the possibility of doing that by quoting for us that a is bigger than 0. If they didn't quote to us a is bigger than 0, we may not be able to deduce something that is like this by multiplying throughout by a, because it may change the inequality sign. So anyway, this is x. So I know x is supposed to be between 0 to A for this. But it can be observed. So you don't necessarily need to write down so much things. I know it is just going to be a 2 marks question. So I'm writing down as an explanation. If you want to cut short your working, I believe it is totally fine also. And at the same time, when t is between 0 to pi over 2, we know that cosine t is also going to be between 0 to 1, where the graph is going to be like this, right? Then we will continue with the cosine graph. So from 0 to pi over 2, inclusive, y, the output is going to be from 0 to 1. So cosine t is from 0 to 1, which means that a times of cosine t is going to be from 0 to a, which means that y is going to be from 0 to a. Okay, so we have the restrictions on x and y here. Let me put it down here also. So we know here x is going to be bigger or equal to 0, less than or equal to a, and y is going to be bigger or equal to 0, less than or equal to a. And part 2, we are supposed to sketch the graph. For sine square to be between 0 to 1, I mean, one of the fastest way is, I guess, a bit more tedious, but I guess one of the fastest way, right, is definitely to go and sketch the graph of y is equal to sine square. But then you will realize that it is between 0 to 1. But another quick way, it is not the best possible way to do this verification. Another quick way is, you know, sine t itself is between 0 to 1. So you can just pick any numbers that are in between. For example, half. Half square is going to be 1/4. You can pick 0.9. 0.9 square, it is still going to be 0.81. So all the numbers that you try to pick here, that is between 0.0 to 1, when you square it, it will still be between 0 to 1. And when you pick 0, you square it is 0. When you pick 1, you square it, it is going to be equal to 1. But that is why we can sort of like deduce that sine square is between 0 to 1. Or else, a better way, definitely better way, is just to simply sketch the graph of sine square. Yep, I think it is no problem, even if you want to make y the subject. Okay, so we don't need to leave it in this form. You can make x the subject, you can make y the subject. But if you were to make y the subject, it is possible. But let's remember that if we were to make y the subject, this is going to be equal to a square minus ax. Then we will go for the positive square root. We will go for the positive square root because y is supposed to be between 0 to a. So if you accidentally put a plus or minus, I believe that you should be incorrect. So, I mean, during the exam, if I were to still take care of this kind of plus minus detail where I got to reject the minus and go for just the plus, I'll probably just leave it as y squared. So at least I don't have to worry about this kind of detail for a 2 marks question. I have tried to put this into my graphing calculator. Let me see whether I have a screenshot. So I have put this into my graphing calculator. Okay, x is this, and I will also, like what I told you guys before, I want to make sure that windows is properly specified. T minimum is from 0, T maximum, this is pi over 2. And the graph that I will be getting is this. Okay, it is this. So let me do a quick sketch based on what I have now. So the y-axis, the x-axis, and we have a graph that is something like this. X, I know it is going to be between 0 to a. Then y is also going to be between 0 to a. So I believe that this should be a. 0, I believe that this should be a. We can do a quick test. For example, when t is equal to 0, I sub it into here. When t equals 0, sub it into here, x is equal to 0. And y is going to be a, cosine 0 is 1. So I will be getting the point when t is equal to 0, I will be getting the point 0a. So 0a is this. So this is the place where t is equal to 0. And t can be equal to 0, so here is going to be a solid dot. Similarly, I can try to put pi over 2 into here. So when I put pi over 2 into here, sine pi over 2 is 1. So a times 1 square is still going to be equal to a. Then cosine pi over 2 is 0. So this point here will generate to a point a, 0, which is here. So I know at this point here, t is equal to pi over 2. Okay. So let me erase this. Is there any more details that I need to put down? Okay, I think this is enough. Okay, I have done the sketch and part 3. Part 3 is part 3 I would say it is a little bit awkward. Let me show you what I have gotten, okay? Because oh, somebody is asking about labeling this, right? Because this is actually on the Cartesian axis. So you can, okay, there are two ways that I will label this. I'll label this as either ax plus y square is equal to a square by just labeling it using this Cartesian, or I can just simply call this as curve C. Oh, yeah, correct. I have missed out this, so there must be a solid dot here. Okay, let me just use C. It is the easiest. So in order for me to sketch, in order for me to understand this, I actually try to plot this into the calculator. And when I try to plot this into the calculator, I've gotten this. Let me show you how I do part 3 of the question. And to get this graph, right? Okay, and to get this graph, I actually plotted it as y1 is equal to square root of, I took a as some random positive number. So for example, 1. So I took y1 as 1 square minus 1 times of x. So I have this, then positive square root. Okay, so y1, I took it as this. Okay, that is when I assume a is equal to, okay, let me just write down. I'm assuming that a is equal to 1, so that I can at least press something into the calculator. So I have a 1 times x plus y square is equal to 1 square. So y is going to be equal to plus minus, and I was telling you that since y is between 0 to 1 in this case, so I'm taking a positive number for it. Then y2, I will of course go for minus x plus 5 over 4. We're taking a as 1, for example, and I got something that is like this. And this is this is a detail that I find personally very difficult to handle during the exam, because I will need to do an analysis to this point. I will need to do a quick analysis to check whether this line here is tangent, or is this line cutting at 2 points, or maybe is this line not even touching this at all. We can do the check by, of course, zooming in, but the best possible way to do the check, I would say, is to solve a simultaneous equation for this. For example, if I have y is equal to y plus x, this is equal to 5 over 4a. Let's say I make x the subject, x is going to be equal to 5 over 4a minus y. I'll call this my first equation. And my second equation will be this ax plus y square. This is equal to a square. So I will have a 5 over 4a minus y plus y square. This is equal to a square. And this will give me a 5 over 4 a square minus ay plus y square. This is equal to a square. So y square minus ay plus 1/4 a square. This is equal to 0. 4y square minus 4ay plus a square. This is equal to 0. And if you were to factorize this, we will have a 2y minus a square. This is equal to 0. So y is going to be equal to half a. So we found out that if I were to solve simultaneous equation between equation number 1 and equation number 2, I will have one point of intersection. That is why this line and this curve, they are actually tangent to each other. We will need to solve the simultaneous equation anyway, because if I'm not able to get the coordinates of the point of intersection, we will not be able to subsequently use integration to find the area that to find the volume that the question is trying to ask us for. So now with this, I know that for this other, let me remove this first. So we now know that for this point here, it is going to be something that is like this. Let's say it is somewhere here. So we have this tangent, then all the way. Okay, so this here is y plus x is equal to 5 over 4a. And we have found out that the y coordinate that is at this point, the y coordinate at this point here is half a. And if y is equal to half a, I'm going to substitute into here. I'm going to find the x coordinate at this point. So I have a half a plus x. This is 5 over 4a. This tells me that x at this point is going to be equal to 5 over 4a minus half a. This is going to be equal to 3 over 4a. So the x coordinate at this point is 3 over 4a. And what the question is asking for is for the region that is bounded by the curve C, this line and the y-axis. So we are looking at this region here. And this region is going to be rotated about the y-axis. Wait, let me erase this first. So now if I were to focus on this region, we will be taking the volume of the cone that is going to be generated. So this will be getting a cone with all this triangle here. It is going to be rotated about the y-axis. Then I'll minus away this portion here of the curve. Okay, this portion of the curve being rotated about the y-axis. So we'll use the cone. It will be 1 over 3 pi. Radius is this. So radius is going to be 3 over 4a square. Height is going to be this point here, the y coordinate at this point. The y coordinate at this point is when x is equal to 0. So the y coordinate at this particular point is 5 over 4a. So this is going to be the height, which is going to be 5 over 4a minus half a, which is actually 3 over 4a. So pi 1/3 pi r square h. Then minus this, I'm going to be making use of integration. I'll be integrating from the lower limit, which is half a, to the upper limit, which is this a. So half a to a of x square dy. And we know what is x square, because for this curve, we have ax plus y square. This is equal to a square. So x is going to be equal to a square minus y square divided by a. So now this is going to be equal to 1 over 3 pi of 3 over 4a times, this is also 3 over 4a, so 3 over 4a to the power of this, minus away pi integration from half a all the way until a of x square, which is a square minus y square divided by a, then square dy. So this is going to be equal to 9/64 pi a cube minus a square. I'm going to take it out. So I have a pi divided by a square, integration from half a all the way until a of this a square minus y square square, which will be a to the power of 4 minus 2a square y square plus y to the power of 4 dy. So I have a 9/64 pi a to the power of 3 minus pi over a. This, it will be a to the power of 4y minus 2a square. This will be y to the power of 3 over 3. Then plus this will be y to the power of 5 over 5 from half a all the way until a. I'm going to leave it to you guys to continue with the substitution. This is the one that is that I find that is sort of like tedious. So a square minus y square. Okay, so I'm going to leave it to you guys to continue with the substitution. Okay, if you have substituted everything correctly, this is going to be 29/960 pi of a to the power of 3, which means that k is equal to 29/260. Yeah, 29/260. I'm so sorry. I'm looking at this question, but I have a I can't really understand this question. Curve square minus curve square. Oh, okay, wait, sorry. I I can understand this question. Yes, you can definitely use curve square minus curve square, which means that instead of using volume of a cone, we just make this x the subject, then after that pi integration from half a all the way until 5/4a, then x squared dy. Okay, you can do that also, but personally I feel that if we can use standard formulas for geometries, we should just try to use the standard formulas. It is usually simpler, you know, than to go for integration. Whoops, this is Alvin, you're right, this is going to be 960. Let me quickly take a look at 6. 6 is actually a pretty easy question. Then let's see whether I have time to just finish off with finish off tonight with question number 7. Because I also want to try to spend a bit more time on the second half of this AJC paper. So if I can just do question number 7 by tonight, that would be great. Okay, let me take a quick look at question number 6. 6 is a pretty easy question. Okay, I have to say it is easy to do as a revision, but again, if this were to happen during the exam, it can be potentially very confusing. So please don't belittle this paper. Okay, it is very difficult to react to a paper that is like this, of this nature, during the exam. This is a piecewise function, which we are going to try to sketch it first. So when it is less than -2, okay, I'm going to press this into the calculator. This has a horizontal asymptote of y equal to 0. So let me code y equal to 0 first. And the first portion, all the way until from -infinity to -2, we will have a graph that is something like this. Okay, all the way until when it is at -2. Then from -2 to 1, it is following this. If I were to just press it into my calculator, I will be getting something that is like this. Here. Then something like this. This is when x is equal to -1. And when y is equal to 0, this point here is -1. And if you were to verify, this is actually on the same horizontal line. So -2 -1, and 0 minus 1. And this point here is when we are at 1. And when you sub 1 in, this is minus 2. And then when x is bigger than 1, it is this curve. And this curve is going to be something like this. So all the way until infinity. And it is cutting here at 2. Okay, so this is my graph of y is equal to fx. Yep, this is a piecewise function, and piecewise function has been gaining a lot of attention these few years because A-level has been setting a few piecewise function questions. And part 2, we are supposed to evaluate this from -3, let's say -3 is somewhere here. From -3 all the way until 4, let's say 4 is somewhere here, which means that you will go all the way up, to somewhere that is on top here. And we are trying to find the exact value of this. And this modulus of fx means whatever that is below the x-axis is going to be reflected up. So in a way, I'm not sure whether the next thing that I'm going to do, the next sketch that I'm going to be doing is confusing, okay? But I'm going to just use another color to do a very quick sketch. So it is going to be reflected up. I will have, this portion here, and we will have something that is like this. Then after that it is this. Okay, so we will have something that is like this, which means that what the question is asking for from -3 to 4 integration of this, if we can just interpret this as a area under the graph. So we are looking at this region here. So basically we are trying to give a value to this region all the way until here. Okay, so it will go all the way up. So all this entire region here. And someone is asking why y equal to 0 is the asymptote because of this. Okay, because when you look at this, when x tends to minus infinity, then y, which is equal to this 6 over x minus 4, is going to tend to 0. So y equal to 0 is the horizontal asymptote on the left hand side. If you were to draw this graph onto your calculator, on your calculator it should look something that is like this. Yes, a vertical asymptote of x is equal to 4, so it will be something that is like this. Okay, so y equal to 0 is going to be the horizontal asymptote. Okay, so anyway, if we were to now see this integration from -3 all the way until 4 of modulus of fx as area of this grayed out region. For this region here, it is like us trying to work on this region from, actually we shouldn't have this. Okay, from -3, okay, sorry, from -3. So it is like this region, but the positive of this region. So if I were to look at this region that is below the x-axis, it is going to be integrating from -3 all the way until -2 of this graph, which is 6 over x minus 4. But I know if I were to just simply do an integration to this, I'm going to be getting a negative value. So I'm going to add a negative in front because I want it to be the absolute area. Then plus this region. This region is just a triangle. So it's going to be half times base 1 times height 1. Half times 1 times 1. Plus this other triangle here. This other triangle is the reflection of this triangle. So it's going to be half times base 2, height 2. Half times 2 times 2. Then plus this region here, which is a reflection of this region. So it is going to be integrating from 1 to 2 of this graph, which is this x squared minus x minus 2. And because when I do this integration, I'm going to be getting a negative value. So I'm going to add a negative in front to make this positive. And plus, of course, from 2 all the way until 4. So integrating from 2 all the way until 4 of x squared minus x minus 2 dx. So this will be minus 6. Integrating 1 over x minus 4 is going to be ln modulus of x minus 4. from minus 3 all the way until minus 2 plus half plus 2. So I have a 5 over 2 minus integration of this, which is going to be 1 over 3 x to the power of 3 minus 1 over 2 x square minus 2x from 1 to 2. The same for this. It is going to be 1 over 3 x to the power of 3 minus 1 over 2 x squared minus 2x from 2 to 4. I'm going to leave you guys again to do the substitution. It can be a bit confusing and probably the rush will cause some careless mistakes here and there in the exam. That is why I do find that this question is not that easy to accomplish during the exam. It will be this, and 6 over 7. Let me give you the answer. This is 37 over 3. Yes, you guys can also, instead of doing a negative, you can definitely just take this and do a modulus. But doing a modulus will be a little bit more dangerous because you are going to be dealing with expression that is like this, and the question asks you for the exact form. So if you want to remove the modulus, you need to know whether you want to assign a plus or minus to it. Okay, because I mean, you just imagine, okay, if you were to be doing a modulus for this, which means that you'll be doing something that is like this, from minus 3 to minus 2 of 6 over x minus 4 dx. While I did a negative, because I know this value here is going to be minus, so algebraically I just get a negative 6 ln 6 over 7. But if you were to do an overall modulus, you'll be getting something that is like this, which is also okay. So you'll be getting a 6 then ln of modulus of x minus 4. Then from minus 3 all the way until minus 2. So you'll be getting a modulus of 6 ln 6 over 7 modulus, which means that you're going to make another decision to add in a negative ln 6 over 7. And this is not an easy decision to make during the exam, because if you are looking at this whole thing as a positive number and ln 6 over 7 is negative, that is why from here to here you add a negative in front. Actually, I hope to end soon. So let me just do one last question, then we will be ending. And for the rest of this paper, we will continue on another. Let me just show you which day I'm going to be. I'm planning for. I'm planning to go for this Friday, 8 p.m. So I'll be doing the harder part of this ASRJC paper on Friday. But in fact, even the first 7 questions, they are difficult. Okay. They are difficult because it is not going to be easy to score for this kind of these 7 questions during the exam under the 3 hours. From 2 to 4, somebody is asking about this 2 to 4. Okay, so from 2 to 4, it should be above the x-axis. It's not below the x-axis because we are doing a modulus of fx. So whatever that is below the x-axis, we will reflect it up. But whatever that is already above the x-axis, we are not going to touch. Modulus is us reflecting whatever that is at the bottom up about the x-axis. Okay. What? Are you sure you feel sad doing this question? I thought this question is actually quite easy. But the problem is the details. Okay, and all the substitution. Okay, anyway, let me very quickly look at question number 7. Okay, let me finish off with question number 7. 7 is not an easy question to do in the exam, definitely. It's a bit tedious, but let me do it a little bit faster. There are a lot of, there are a lot of times when I think doing a question that is like 7 where we may accidentally introduce some kind of careless mistakes into our solution also. So I want to try to be a bit more careful while showing you this question number 7, but at the same time, let me try to do it a little bit faster. And if you guys are doing this together with me, right, let's see whether we can do this a little bit faster together. Okay. So we are looking at a quadratic equation, z squared plus 2 minus 2i z. This is equal to minus 3 minus 2i. And I was telling, I was saying during my tuition, during my weekly tuition classes, that when you are looking at a polynomial, and if it is a quadratic polynomial, it is actually pretty safe to work on the quadratic polynomial, because you can always find ways to solve a quadratic polynomial, even if you cannot do ultimately you always have that formula that's going to work for all quadratic formula, regardless of whether the coefficients are real or whether the coefficients are complex. That is like this, we can always make use of the quadratic formula. So I'm going to try to make use of the quadratic formula by re-expressing this as x squared plus 2 minus 2i z, then plus 3 plus 2i. Oh, okay. You are set doing this paper and not just question number 6. Okay, so if I were to apply the quadratic formula, it is going to be minus b plus or minus square root of b squared, 2 minus 2i squared, minus 4ac, c is 3 plus 2i. This divided by 2aa is 1. We are not supposed to be using too much of our calculator, or at least in our presentation we do want to show that we are using our calculator. So this is going to be equal to minus 2 plus 2i plus or minus square root of this is going to be 4 minus 8i, then minus 4 minus 12, 4 times this minus 12, then this is going to be equal to minus 8i divided by 2. This gives me this will give me a minus 2 plus 2i plus or minus square root of, plus or minus square root of this can be cancelled, so I will have a minus 12 minus 8i minus 8i is minus 16i divided by 2. Minus 2 plus 2i, I'm going to factorize out 4, square root of 4 is going to be 2. So 2 square root of, since I factorize out 4, I will have a minus 3 minus 4i. This divided by 2. So z is going to be equal to this divided by 2. I will have a minus 1 plus I plus or minus square root of minus 3 minus 4i. If we can, if we have our calculator, I will probably just press this into our calculator, which will work. Square root of negative 3 minus 4i. Okay, I'll just press it into my graphing calculator. But since we cannot use our calculator, my suggestion is to work on this separately by, for example, letting x plus iy be equal to square root of minus 3 minus 4i. I have an intention, that is to re-express this in the form of Cartesian. So when it is in Cartesian, then I can combine with minus 1 plus I to get me the 2 roots of z. I'm expecting 2 roots because z is a quadratic polynomial. So squaring both sides, I have x squared plus 2ixy minus y squared. This is minus 3 minus 4i. So we have x squared minus y squared, then I of 2xy. This is minus 3 minus 4i. So matching the left and right hand side, we know that x squared minus y squared, this is equal to minus 3. And we have a 2xy, this is equal to minus 4. Which means that y is equal to minus 2 over x, which I can then substitute into this, which will give me x squared minus y squared, 4 over x squared is equal to minus 3. Multiplying throughout by x squared, I will have x to the power of 4 minus 3 squared. I'll bring it over to the left hand side. So I have this minus 4, this is equal to 0. So I have x squared plus 4 and x squared minus 1. This is equal to 0. X squared plus 4 is always going to be positive. So for this times this to be 0, it will be x squared to be equal to 1. So x is going to be equal to plus or minus 1. And if x is plus or minus 1, I know y is going to be minus 2. Okay, I should probably write this properly. So from here, when x is equal to minus 1, that means y is going to be minus 2 divided by minus 1. This is equal to 2. So, which means that square root of minus 3 minus 4i. This will be minus 1 plus 2i. Then, when x is equal to 1, y will be minus 2 over 1. This is minus 2, which means that square root of minus 3 minus 4i. This is going to be equal to 1 minus 2i. In a way, they are just negative of each other, right? Because I can see this as negative of minus 1 plus 2i. So now, this is going to be equal to minus 1 plus i, plus or minus this or this. Oops, I realized I erased this also. So it is minus of minus 1 plus 2i. Okay, so they are negative of each other, which means that this is going to be plus or minus. Let me choose either one of them. Let's say minus 1 plus 2i. So I will have two roots. Z is either minus 1 plus I, minus 1 minus 2i, or minus 1 plus I, minus minus become plus, so plus minus 2i. So I have my two roots. They are minus 2, oops, this is a plus. So minus 2 plus 3i, or the other one is going to be equal to minus I. So I'm going to call this, let's say Z1, and I'll call this, let's say Z2. Let me record down my answers here, okay? So Z1 is equal to minus 2 plus 3i. And Z2, this is minus I. Okay? And as for part 2, what are the other two roots? This is pretty simple. If Z1 and Z2, these two numbers, are the roots of this equation, and for this equation over here, we are looking at a polynomial with real coefficient. If a polynomial that has real coefficient has complex roots, that means the conjugate of these roots will also be the root of, the conjugate of these complex numbers will also be the root of this polynomial. So what are the other roots? The other roots will be conjugate of this, minus 2 minus 3i, and then the other one will be I, okay, because the coefficients are all real numbers. That is for part 2. An explanation will be 1 mark, then quoting this will be, these two will be another mark. What that is a little bit more interesting is minus 3 minus 2i. What is a bit more interesting is part 3. Because part 3, I think when we were doing the VJC paper, I share with you another strategy also on how to do questions that are like this, especially if it is one that is not very easily observable. Like for example, this question, I think the one that was from VJC, it was still not bad because it's at least easier for you to observe what you're going to be replacing the Z with. Okay, so let me show you a strategy, and it can work pretty consistently. So from the very first part, right, we have this. Okay, let me make this a little bit bigger. So from the very first part, we know this, and the roots of this are Z1 and Z2, so they are these two numbers. And now we are looking at this Z squared, part 3. Part 3, we are looking at Z squared plus 2 plus 2i Z. This is equal to 3 plus 2i. Okay, I'm going to show you a strategy And if some of you were here during the VJC paper, you would have seen me using the same strategy also. What a lot of people fail to do, I mean, the reason why some people fail to do this kind of question is that they have this tendency to look at z square and z square. That means they have this tendency to look from the biggest power to the smaller power. But it is actually easier if we were to start with the one that has the smallest power of z, because that is actually the simplest. What I know is that all this z here, when it is being translated to here, they will be re-expressed as some kind of compounded expression in terms of z. So this is supposed to happen. Okay, so which means that the one that is not going to be replaced in this equation, to get this equation, will be the term that is independent of z. That is why this term should remain consistent. It should not change regardless of whether you go from here to, I mean, it should not be changing when you're trying to go from here to here. So looking at this, which is in part 3, I know this, which is independent of z, should look like minus 3 minus 2i. So I'm going to focus on this first by multiplying throughout by minus 1. So I will get this, then minus 2 plus 2i z. This is going to be minus 3 minus 2i. So I've already made one of the conditions satisfied, which means that the term that is independent of z is supposed to be, is not supposed to change. Then I'm going to work on another term. The next term will be the next smallest term in terms of z, which is z to the power of 1. Okay, z to the power of 1. And I know this over here, it is ultimately going to be changed into something that is like this, into something that is like 2 minus 2i, where this entire term here is supposed to be changed into this, where z is going to be replaced by something times z, a compounded expression of z. So I know this has to become this, which means that this hints to me that this minus 2 plus 2i is supposed to become this 2 minus 2i times a, which means that a is going to be equal to minus 2 plus 2i divided by 2 minus 2i. So this will tell me what a is. Here I'm going to just press the calculator. Okay, no one will know that we have pressed the calculator. If I've pressed the calculator, this is going to get you let me see what I'm going to be getting. This will get you a minus I. So I am suspecting now that I have something that is like this, because this can now be re-expressed as plus 2 minus 2i multiplied by a, which I'm suspecting is minus i. Sorry, minus iz. This is minus 3 minus 2i. Okay. So I'm suspecting that it is minus iz. And it's very difficult to see this minus I. So if I can just work from the term that is independent, and then after that the term z, then I'm suspecting that all the z here is going to be replaced by minus iz. Then now I work on this. This is supposed to be minus z squared. And what if z is really replaced by this minus I? Am I going to be getting it? So if this z is really going to become this, so this square, minus iz squared is minus z squared. So I can now re-express this entire thing into this 2 minus 2i, then minus iz. This is minus 3 minus 2i. So I know all the z here are going to be replaced by minus iz. So minus iz is going to be z1 minus 2 plus 3i, and minus iz is going to be equal to minus I. So z is going to be equal to 1, z is going to be equal to minus 2 plus 3i divided by minus I. I'm going to rationalize this by multiplying by I in the numerator and the denominator. This will give me a minus 3 minus 2i. Okay. So please remember my strategy. Okay, this is the second time that we are doing this strategy during the live stream. We will focus on the term that is independent of z first. Where many times when it is this kind of question, where you know z is going to be replaced by some expression, where I'm very sure those of you who didn't manage to observe what you are supposed to replace z with, is usually because you immediately try it with the term that is the highest power of z. And you just imagine when z is going to be, when z here is going to be replaced by a compounded expression of z to get this, and working on that compounded expression square is actually more difficult than working on the term that has the least power of z, because there will be the least possible change, which means that it is the easiest for you to do the observation. Okay, that is why, let me just very quickly explain again, okay, in case some of you didn't manage to catch it. I will work on the term that is independent of z first to make it look like this. That's why I multiply this entire equation here by -1, so I can get at least this to synchronize with this. The next thing I'm going to do is I'm going to synchronize this term here. We synchronize this. So I know this entire term should ultimately become something that is like 2 minus 2i as the coefficient, then a compounded expression of z. So by matching this to this, I know minus 2 plus 2i is going to become this, which will then help me to find a immediately, where I don't need to depend so much on my observation, especially when my observation failed. Then I get a to be equal to minus I. So I know this entire expression can be re-expressed into this, where a is minus I. So I'm already suspecting that z is going to be replaced by minus I z. And if I were to just replace this, by minus I z, square it, I will get back this. So I know all the z. So I know all this z here will be replaced by minus I z, including z1, including z2. So I can get my answer like really fast. I didn't replace this minus z square by minus I z. I replaced this z here. I replace this z here. So we are replacing all this z here by minus I z. I replace this z here by minus I z. Okay, so whatever I'm doing, I'm not replacing this z. I'm just re-expressing this entire, for example, this entire expression here. I'm just trying to re-express this entire expression so that it can look something that is like this. Okay, so I'm not replacing this, sorry, in case I say wrongly, in case I was confusing just now, I was replacing this z here. Okay, this z I'm replacing by minus I z, this z I'm replacing by minus I z. And when I replace this z by minus I z, I will get a z square. So the first part of this question is actually a very, very simple question. It is just a 1-mark question. It is almost the same as what we have experienced in our secondary school. So I don't suggest that we spend too much time doing this question like our secondary school. If you guys know about the cover-up rule, I would suggest that we try to adopt and make use of the cover-up rule for this question number 8, part 1, since it's a 1-mark question. So if I were to make use of the cover-up rule, I am not sure whether you are familiar enough with it. But in case you are curious about the cover-up rule, I did talk about it on Achevas TV in one of the theory outline probably under Summation. I actually talked about this cover-up rule. So if I were to do part 1 by making use of the cover-up rule, so let me just write down this here by cover-up rule. If I were to make use of the cover-up rule, I can actually find a immediately by looking at the value that caused the value of r that caused the denominator to be equal to 0, and that is when r is equal to minus 2, and I'm going to cover up r plus 2. So math equal celebration. Now I wonder if you are from my tuition class, because I remember last Sunday during tuition, I was suggesting to them about whether we should continue with our math tuition this Sunday since it's National Day. Then some people, they were suggesting that we should just go ahead, because they find math more interesting than staying home or something. I don't really know. But anyway, I'm going to make use of the cover-up rule, letting r be equal to minus 2, which caused the denominator to be equal to 0. Then covering up r minus 2, replacing all the r by minus 2, that will give me a. So it is going to be equal to 3 multiplied by r, which is minus 2 plus 4. And this is going to be divided by minus 2 plus 1. And then r, which is minus 2. And a here is going to be equal to minus 1. I'll do the same thing for b. B, for B, we will once again make use of the cover-up rule by replacing the r here by -1, because -1 is going to cause the denominator to be equal to 0, and covering up r plus 1, which cause the denominator to be 0, I'm going to replace all the r by -1. So it is going to be 3 times of -1 plus 4, and this divided by -1 plus 2 multiplied by -1. So we are going to be getting B is equal to -1, and similarly we will find C by letting r be equal to 0. So it is this here. I'm going to let r here be equal to 0, and I'll replace all the r here by 0, and of course covering up r here. So it is going to be 3 times of 0 plus 4, and this is going to be divided by 0 plus 2, then 0 plus 1. And this is equal to 2. So now we have A, B, C, and we are supposed to, A, B, C are constants to be determined. We want to show that this can be written in this form. Let me just jot it down here. We will be making use of it later on anyway. So A is -1. So we have a -1 over r plus 2. Then B is -1 also. So -1 over r plus 1. And C is 2. So 2 over r. We will probably be making use of this since this is a summation question that is in H2 math. So very likely we will be making use of this, and there's a good chance that it is going to be evaluation of this through the method of difference. So let's see whether we are going to be able to apply that. We have a 7 over 3 times 2 times 1, then plus 10 over 4 times 3 times 2, then plus 13 over 5 times 4 times 3, all the way until the last term, which is going to be, according to the question, the nth term. If I can just rewrite this into the summation notation using this as the hint, if I were to use this as the hint, I guess we can try to let r starts from 1 and ending at n, because it will be from the first term all the way until the nth term that the question is saying. And if I were to just rewrite this, let's do that first. So it is this divided by r plus 2 multiplied by r plus 1 times r. Let's do a quick verification. If I were to let r be equal to 1, then the numerator will be 3 plus 4, which is 7. Then 1 plus 2, which is 3, 1 plus 1, which is 1. Then 1 is synchronized to this. If I were to let r be equal to 2, then it will be 3 times 2, 6 plus 4, it is 10. Then this will become 4, this will become 3, this will become 2. It's synchronized. So I am having a summation. I'm rewriting this summation into the sigma notation, which is this, which means that we can now try to make use of this to re-express the summation notation further. So I will have this, re-expressing this using part 1. It is -1 over r plus 2, -1 over r plus 1, plus 2 over r. And very likely it is going to be evaluated through the method of difference. And I would really suggest that whoever you are, right, you should try to work on this cover-up rule. We are using it as a rule. I mean, later if there's some, okay, I think we better don't waste time. There's more questions that we can do here. So I'm going to leave it to you to go and check out this cover-up rule, but I will encourage you to really go and check it out instead of using what you can also do using your secondary school's strategy by multiplying throughout by the this denominator here. Okay, then you will still end up with the same values as -1 plus 2. But because it is so fast, your solution will be way more efficient if you want to write down one that is that can justify for you this 1 mark. So anyway, please check it out, okay? I think it is going to be useful for your A-levels, especially if you are one of those people who are taking the A-levels this year. So we are going to try to evaluate this by making use of the method of difference. By substituting r is equal to 1, I will have a -1 over. By substituting r is equal to 1, this is going to be equal to 3 minus, then this is going to be 1 over 2 plus 2 over 1. Then by substituting r to be equal to 2, I'm going to write it in another row. I have a 1 over 4 minus away 1 over 3, then plus 2 over 2. Minus this will be 1 over 5 when r is equal to 3. Then minus away 1 over 4, then plus 2 over 3. So I'm starting to see a cancellation, which is this, they can be cancelled. But let's hang on a second. Your method of difference is not about subtraction. It is about us trying to find a pattern. So seeing this is not yet a pattern. So let me continue to write one more row. This will be 1 over 6. This will be 1 over 5. And this will be 2 over 4. And now I'm starting to see a pattern. I can see that the cancellation goes this way. So I'm suspecting that 3 rows is going to give me this kind of cancellation. And I'm going to justify that this pattern is going to continue all the way until the last row. So I'm going to write down the last 3 rows to see whether this same pattern is going to continue. So the last 3 rows, the third last row, it will be when r is equal to n minus 2. Then after that, r is equal to n minus 1. And finally, we will let r be equal to n. So this will be the last 3 rows. When r is equal to n minus 2, then we will have a minus 1 over n minus 2 plus 2n. Then minus 1 over n minus 2 plus 1, n minus 1. Then plus 2 over n minus 2. Then minus away when r is equal to n minus 1. Then this will be 1 over n plus 1 minus 1 over n. Then plus 2 over n minus 1. And finally, we have a minus 1 over n plus 2 minus 1 over n plus 1 plus 2 over n. And we are still seeing the same pattern of cancellation. So seeing this pattern continuing all the way until the last 3 rows gives me the assurance that in between will all be removed through the same pattern of cancellation. So we are going to be left with this portion here and this portion here. Okay, so we are going to be left with this. So it is going to be minus 2 plus 2 over 1 plus 2 over 2. Then minus away 1 over n plus 1, minus away 1 over n plus 2, then minus 1 over n plus 1. And this is going to be equal to 3 minus half. This is 5 over 2. Then minus away this and this. If I were to combine, that is 2 over n plus 1. Then minus 1 over n plus 2. Okay. So, okay, so we have this, and this is going to give us our answer for this summation here. Let me write it down also. So we know that this, which is going to be equal to the summation of 3r plus 4 over r plus 2, then r plus 1 times r, and starting from r is equal to 1 all the way until n. The result for this, like what we have just written down here, let me write it down here. So the result is going to be equal to 5 over 2 minus 2 over n plus 1 minus 1 over n plus 2. Okay. So this is part 2 of the question, and hence we are supposed to show the very last part. And now I am so tempted to just quickly go through this cover-up rule, because I am seeing like the two of you here discussing about the cover-up rule. I feel that it is I mean, you should definitely make use of the cover-up rule. It is not just that it is fast. Is that if you are still going through your secondary school strategy, right, in the end you are going one circle and you are going to get exactly the same thing. So I'm so sorry, okay, I don't plan to go through this cover-up rule, but can I just have like maybe 30 seconds, okay, 1 minute of your time? Let me just very quickly show you why just now when I make use of cover-up rule, I sort of like managed to find A immediately by covering up this, right? I cover up this. Then A is, and replacing all the R here by minus 2. So this is 3 times of minus 2 plus 4 divided by, we are covering up this, right? So it is minus 2 plus 1. Okay, then multiply by R, which is minus 2. Again, this gave us A, which is minus 1. Okay, so we did it as a cover-up rule. Okay, and this is very fast. But what if we don't do this as cover-up rule? That means we will be executing just like how we did it in our secondary school, which means that I will multiply this throughout by r plus 2r plus 1 times r. This will give me a 3r plus 4. This is equal to 4 times of r plus 1 times r. Sorry, not 4 times. This will be a times. Okay, let me erase this. Oh no, okay. So this will be a times of this plus b times of r plus 2 times r, then plus c times of r plus 2 times r plus 1. Okay, so we have gotten this. What would you do to find a? So to find a, how about letting r be equal to minus 2? Okay, I'll let r be minus 2. So this will be 3 times minus 2 plus 4 is equal to a times of minus 2 plus 1 times r, which is minus 2. And this will disappear, right? Because you purposely let r be equal to minus 2 so that this term will become 0. This term will become 0. And now we can find a, right? We can find a. And what is a? A is 3 times of minus 2 plus 4 divided by minus 2 plus 1, then times minus 2. And this is minus 1. And can't you tell that after going through this one huge round, in the end, you are actually writing down exactly the same thing? You know, that is why cover-up rule is actually very fast. It saves you the trouble of writing all this thing, because you can actually see the same rule being applied every time when this kind of condition exists. Okay, that is why I will really encourage you guys to use the cover-up rule, especially when we are doing summation question, when we are working on integration technique question. You know, when we are working on these few kinds of question, many times you will realize that by making use of cover-up rule, we can sort of like re-express the partial fraction, like just simply pressing the numbers into our calculator. We may not even need to write down the workings, because partial fraction in H2 math gives very little value in terms of the marks that we are going to be awarded. Okay, like here is going to be 1 mark. If it is going to be within an integration technique question, sometimes they don't even allocate a proper 1 mark, maybe just half mark to your integration technique. So anyway, we have this as our result, and in part 3, we are supposed to hence show this. So part 3, now we are looking at another summation. Let me just very quickly write down this other summation. We are summing from r is equal to 5 all the way until n plus 3. From 5 all the way until n plus 3 of 3r minus 5 over r minus 1 multiplied by r minus 2 multiplied by r minus 3. We are supposed to discuss and show that this is less than 4 over 3. And what I'm very sure of is that we are going to be making use of the previous summation notation here, this previous sigma notation here, but sadly the expression that is within the sigma notation, they do not look the same. So I'm going to make use of another rule, this time not as easy as the cover-up rule, but it is not difficult for us to implement, which is a rule that I believe a lot of you have probably seen it in your school's lectures or so. I'm going to make use of the rule that I put onto the Achevas TV, which is, let me show you guys, okay, which is this rule here. Let me blow it up a little bit. Okay, I'm going to make use of this rule. Okay, let me make it even bigger. Okay, I'm going to make use of this rule here. I think it is very, very useful. This time I am very sure I am not going to try to explain to you the rule. Let's just make use of the rule by itself, okay? So if I were to make use of these few rules here, specifically 4 and 5, what we can try to do is to re-express this into a form that looks as similar to this as possible. And what I can observe is that if I were to replace the r in the denominator by r plus 3, r plus 3 minus 1 is going to give me a r plus 2. R plus 3 minus 2 is going to give me a r plus 1. And r plus 3 is going to give me r. And to do that, I am going to make use of this number 5. I'm going to make use of this rule to replace r by r plus p. And in this case, I'm going to be replacing the r by r plus 3. So this is going to be equal to 5. And according to this rule, if I were to plus p, the number that is on top here, we will minus p. So the number that is on top is n plus 3, and this I will minus 3. And I'm going to continue to replace all the r by r plus 3, then minus 5 divided by r plus 3 minus 1, that will give me a r plus 2. Then r plus 3 minus 2, this gives me a r plus 1. R plus 3 minus 3, this gives me r. So I am going to be left with plus 3. I'm going to bring it over to the other side. This will be r is equal to 2. Then this will be n. And here I have a 3r. Then plus 9 minus 5. It is going to be plus 4. This is going to be divided by r plus 2. Then r plus 1. Then r. So I'm getting the same expression that is within the sigma notation as what I've gotten in part 2. But now it is starting from 2 instead of starting from 1. So I'm going to break up my summation by now making use of number 4. So if I were to sum from r is equal to 1 all the way until n of 3r plus 4 divided by r plus 2, then r plus 1 times r. If I were to sum from the first term all the way until the nth term, to get this, which is from the second term all the way until the nth term, I will need to have this minus off the first term, which is when r is equal to 1. That will be 3 times 1 plus 4 divided by 1 plus 2, then 1 plus 1, then times 1. Let me shift this away a little bit. Okay, so now with this, I am going to replace it by 5 over 2 minus 2 over n plus 1 minus 1 over n plus 2. And if I were to press this into the calculator, I'm going to be getting a 7 over 6. So now we will be getting this as a 4 over 3 minus 2 over n plus 1 minus 1 over n plus 2. And now it seems pretty obvious, right? It seems pretty obvious to us that this expression here is going to be less than 4 over 3. But I think for a lot of your schools, they require a slightly more rigorous discussion than to just simply through observation, this is less than 4 over 3. So what I suggest that you can do in terms of your presentation to make your discussion a little bit more rigorous is to discuss for the fact that n is supposed, when it is bigger or equal to 1, because when it is negative numbers, this what I'm going to be writing next may not be true. And why n is bigger or equal to 1? Because r starts from 1 all the way until n, which means that the smallest possible the number n can go will be 1. So when n is bigger or equal to 1, we can see that the term minus 2 over n plus 1 minus 1 over n plus 2, this is going to be a term that is less than 0. And if I were to plus 4 over 3 on both left and right hand side, so this 2 over n plus 1 minus 1 over n plus 2 is less than 4 over 3. So plus 4 over 3 on both sides, and this can be traced back all the way until here. So therefore, we can now say that the summation from r equal to 5 all the way until n plus 3 of 3r minus 5 divided by r minus 1, r minus 2, and r minus 3. This, which I trace back to this, is less than 4 over 3 and hence shown. Okay? Hang on. Let me take a look at some of the things that you guys have mentioned. You know, the cover up rule that I have just shown you. There are actually a few different versions of cover up rule, but I think the safer one that you can try to make use of cover up rule is when the denominators are all linear expression. If they were to be quadratic, there is another kind of rule which is also part of cover up rule, but I don't suggest that you try to use cover up rule because you don't really exploit much. So my suggestion is only when the denominators are all linear, multiples of linear expression, or must be linear expression, then you apply the cover-up rule, or else just do what you have already done since your secondary school. To do the reverse, in a way, yes. If you were to do the reverse, I would say that it is very similar to what you have already done in your secondary school, which is to, group all this together to become one single term. And when you group all this together, it is the same as what I did just now. When I try to multiply throughout by the denominator, and I'll try to substitute and replace different values of r to get a, b, c. This is obtained from here, right? I simply just evaluated this minus 7/6. 7/6 is going to be from here. So this minus 7/6, that gives me 4/3 minus 2/n plus 1 and minus 1/n plus 2. I don't think we can discuss about n going to infinity because this is not a sum to infinity question. So we cannot just simply let n goes to infinity. That means what this question is suggesting, right, is that even when n is equal to 7, this is going to be true. Even when n is equal to 10, this is going to be true. Even when n is equal to 2, this is going to be true. So I cannot just simply let n goes to infinity to say that this is less than 4. Because this is not a discussion on convergence. This ends at n plus 3. Okay, let me move on to question number 8. 8 is also pretty okay. Maybe except the last part of this question number 8. Sorry, I mean 9. 9 is pretty okay, except the last part of question number 9 maybe. But the last part is not like it is very difficult. It's just to me I find it a bit unexpected to see the last part of this question number 9. Usually questions don't ask in that way. So anyway, let's take a look at this question number 9. We saw something that is similar to this where a diagram was given to us, I think in the A-levels last year or last year. So so it is usually when diagrams that are like this, 3D diagrams that are like this are given to us by the question, the intention is not exactly so much for visualization. It is more of like for you to read the coordinates directly from the diagram. So it's usually just to read the coordinates. Okay, I sometimes I do feel that the diagram makes the visualization even more difficult. Okay, so let's take a look at the information that is given. We have this diagram with an object with O as the center of the rectangular base, A, B, C, D. And we are given that A, B here is 8. And we are given that BC is 4. So this is 4. Let me just write it down here, okay, since this is a rectangular base. And the top side of the object, this EFGH, is a square with the sides as 2. So this is 2, this is 2. And it is parallel to the base. The center of the top side is vertically above O and the height is H. So if I were to say that this is the center, for example, if this is the center of the top side, then this length here that we are talking about, this length here is a length of H. So part 1, we are supposed to show that the equation of the line that passes through B and G follows this. The equation, Alvin has mentioned that it is in the year 2018 where a question that is similar to this appear in the A-levels. So I mean you guys can go and take a look. Okay, anyway, part 1. I'm going to try to form the equation of a line that passes through B G. So I am going to write down the position vector of B. Like what I was telling you, many times the diagram that is given to you is more of like for us to be reading the coordinates instead of trying to do the visualization. So for OB, that will be moving in the I direction by 4 units. Then after that, moving in the J direction, opposite the J direction, by another 2 units. And in the K direction, there's no movement. So OB will be positive 4. Then opposite J, so minus 2. Then nothing in the K direction, so 0. Then OG, vector OG. As for vector OG, if we were to start from O, we want to reach here, so we'll go by 1 unit. It's like as if it is here, 1 unit. Then after that, 1 unit. It is as if it is here, then here. Then after that, we'll go vertically up by K units. So 1, 1, H. So H units. So moving this is going to be positive 1. Hang on. So this is going to be positive 1. Then moving in the opposite direction from J by 1 unit, it is minus 1. And vertically up by H units, so this is going to be equal to H. Okay, let me just erase this. So let me redraw this. H will be from O all the way until here. So this is H. So once again, for OG, it is going to be 1 minus 1, then H. Okay, so now with this, we can find the vector. We can find the vector BG, because vector BG is going to be a vector that is parallel to the line that passes through B and G. So OG will be 1 minus 1 H. Minus away OB, which is 4 minus 2, 0. And this is going to be equal to minus 3, 1, and H. So therefore, we can see that the line that passes through B and G, this will be R is equal to, I can make use of the position vector of B or the position vector of G, according to what the question wants me to show. Very obviously, they have asked me to make use of the position vector of B. So I'm going to make use of this 4 minus 2, 0, plus T of the direction, minus 3, 1, H. Okay, so let me write down some of the information that we have so far. So we know OB here is, we have deduced it to be 4 minus 2, 0. And OG over here, this is 1 minus 1 H. And the equation of the line L, the equation of the line that passes through B and G, it is going to be equal to this. Next, I want to find the sine of the angle. Let me erase this a little bit. Hang on, maybe I should bring this down. Okay, let me erase this a little bit. Next, we want to find the sine of the angle. The sine of the angle that is between BG, the line BG, and the rectangular base ABCD. So for part 2, sine of the angle that is between the line that passes through B and G and the rectangular base. So I'm going to take this as the rectangular base. We are supposed to find this angle. I'm going to call this angle theta. And in order for us to find this angle, I'm going to use a strategy that I try to highlight on the Achevas TV. We will not try to find this angle directly. We will try to find this angle, or to try to find the sine of this angle indirectly by referencing it based on the direction that the line is parallel to. The line is parallel to minus 3, 1, H. And as for the plane, this plane ABCD, I'm going to work on its normal vector. Its normal vector can be one that is parallel to K. So I shall just go for a 0, 0, 1. So what I'm going to try do is to work on this angle here, which is going to be 90 degrees minus away the angle theta. So with this as my reference instead of directly theta, I can now make use of the dot product. If I were to make use of the dot product, I will be looking at a minus 31h. Then this dot 001, this is equal to modulus of minus 31h modulus of 001. Then cosine of the angle that is between these two vectors, that is 90 degrees minus theta. And in trigonometric identity, okay, let me just very quickly explain this again, because I'm also expecting some of us probably we have a bit of problem seeing this OG. First of all, you, like what I was saying just now, right? You should be making use of the diagram. Most likely, okay, when this kind of question appear, you should be making use of the diagram to read coordinates of points. Okay, so let me try to quickly explain how I get OG one more time, because G is vertically above a point that is somewhere here, let's say. So G is vertically above a point that is here. So to get from O to G, we will move here, then we'll move here, then we'll move up. So it is going to be this, this, then this. So what is the distance that you move from here to here? And please remember, okay, all these are perpendicular to each other. So from here to here, because this is 2 units. So from here to here it is, from here to here it is like from here to here. So it is 1 unit. So 1. Then after that here, it is also another 1 unit like this. Another 1 unit, but you're moving opposite from J. So minus 1. Then after that you're moving up, which is the same as H. So H. So 1 minus 1 and H. Okay. Anyway, coming back to this question here, using secondary school's trigonometric transformation, we know this is sine theta, because we know complementary angle 90 degrees minus theta. So sine 90 degrees minus theta is cosine theta, and here cosine 90 degrees minus theta is sine theta. Tangent 90 degrees minus theta is cotangent theta. So now we have this, and if I were to execute the dot product, this is going to be equal to h. This is going to be square root of 3 square plus 1 square, so 9 plus 1, 10. Then plus h square. Square root of 1 is still going to be 1. And now I can write this as sine theta. So sine theta is h over the square root of 10 plus h square. Okay, so this is for part 2 of the question. And as for this 001 that I'm using here, this 001, it is the normal to the plane A, the plane that passes through A, B, C, D. So since this plane is flat on the ground, the normal vector must be parallel to K, and a vector that is parallel to K can be 001. Next, now we have found sine theta. Let's take a look at part 3. For part 3, goodness, this is such a long question, and I'm trying to refer back to the solution. To the question. So difficult to manipulate within this space here. So let me move this here. Okay. Hang on, let me just shift this a little bit. Okay, now we want to try to find the Cartesian equation of the plane BCFG. Wait, can I just shift this a little bit more? Okay, so we want to find the equation of the plane BCFG. So we need the normal vector, and to find the normal vector of BCFG, actually we are supposed to let h be equal to 6. So from this point onwards, h is equal to 6. Let me rewrite our OB. So OB is going to be, OB is still 4 minus 2, 0. No change, but OG is the one that has changed. So OG is going to be 1 minus 1h, which is 6. So I mean, and in part 3, let me do it here, part 3, we are supposed to find the Cartesian equation of the plane B, C, F, G. So I'm going to make use of two vectors that are parallel to this plane. Cross them, that will give me a normal vector. One vector that I guess I'm going to try to make use of is a vector that is parallel to BC. A vector that is parallel to BC will be parallel to J, correct? A vector that is parallel to BC will be parallel to J. So I'm going to make use of the vector as 0, 1, 0. A vector that is parallel to J. So let me write it down here. Another vector that I'm going to make use of that is parallel to BCFG. I guess I'm going to make use of BG, the vector BG, which just now we have found it is the same vector that is parallel to the line that passes through BG. So for BG, since h is equal to 6, now we will be looking at it as minus 316. So minus 316 here. If I were to cross these two vectors, minus 316, this should give me a vector that is normal to the plane that we are looking at. So this, if I were to cover up the first row, 1 times 6, this is going to be 6, then 0. And covering up the second row, we have 0, 0. So 0. Covering up the third row, we have a 0 minus 3. It's going to be positive 3. So this is going to be a vector that is perpendicular to the plane. Or I can also factorize out 3. 2, 0, 1 is also going to be perpendicular to the plane. So now we know for this plane that passes through B, C, F, G, the dot product, in its dot product form, it will be R dot the normal vector. We can use 6, 0, 3, or we can also make use of 2, 0, 1. Both are going to be normal to this plane, and this is going to be equal to, I'm going to take a point that is on this plane. I can take B, I can take C, which is easy. I can take G, but let me just go for B. B has a position vector of 4, minus 2, 0. So this dot, the normal vector 2, 0, 1, this is equal to 8. And then replacing R by X, Y, Z, expanding the dot product, we will have a 2X plus 0Y plus 1 times of Z. This is equal to 8. So this is the Cartesian equation of the plane that passes through B, C, F, G. And we want to find the shortest possible distance from the point A to this plane B, C, F, G. From the point A to the plane B, C, F, G. And for this plane B, C, F, G, we know it is R dot 2, 0, 1. Okay, this is equal to 8. So the shortest possible distance, let me just do a quick sketch of the scenario first. So for part 4, we are looking at the shortest possible distance from A. And as for this point A, we can actually highlight the coordinate A. The coordinate will be minus, because this length is 8. So it will be minus 4, then minus 2, and 0. Correct? A will be minus 4, minus 2, and 0, because this length is 8. So here is going to be 4. This length is 2. This length is 4. So this length is going to be equal to 2. So this is 4. This is 2, and it didn't go in any, it didn't clock any direction that is in the K. So A will have a coordinate of minus 4, minus 2, and 0. And we are supposed to find the shortest possible distance from A to the plane, let me draw it here, to the plane that passes through B, C, F, G, which we know that this plane is R dot 2, 0, 1. This is equal to 8. And we are supposed to find this distance here, 90 degrees. And I think was it last week or last week, we actually made use of a formula that I was telling you it is ridiculously useful. We are going to be making use of that again. You can find this formula on the Achevas TV. Again, I'm not going to explain about why this formula looks like this. You can take a look at the video on the Achevas TV. But I'm going to be making use of this. Okay, I'm going to be making use of this formula here to find it is the formula that can help us to find the distance between two parallel planes. And during that session when I talk about it, I was telling you how useful this formula is, and we are now actually making use of it the second time already. This formula, the distance between two parallel planes. How can I make use of the formula to find the distance between two parallel planes for this? How can I do that quickly and easily? What we can try to do is to just simulate another plane that is going to be parallel to this plane and passes through the point A. I am going to call this plane, for example, pi A. Okay, I'm going to call this plane pi A. And it is very, very easy for us to form the equation of pi A. Because for pi A, the equation will be r dot a normal vector to pi A. Since these two planes, they are parallel to each other, so I might as well just make use of this to represent the normal vector to this plane. And this is going to be equal to taking the position vector of a point that is on this plane, minus 4, minus 2, 0, dot 2, 0, 1. This is going to get me a minus 8. Okay, so this gives me a minus 8, and now I have the equation of this plane, I have the equation of this plane. We can then find the distance that is between the two parallel planes, which will then give us the distance that is between A and the plane, the shortest possible distance between A and the plane. So making use of this equation, it is going to be modulus of, and like what I try to warn us is we should try to retain the original plus or minus, the original signs of the two p's, which is this value here. So if I were to start with this, I will retain minus 8 divided by modulus of the normal vector, which is 2, 0, 1. And minus away, the other one is 8. Then over modulus of 2, 0, 1. This will be modulus of minus 8 divided by, this is going to be square root of 2 square plus 0 square plus 1 square, sorry, minus 16. So this is going to be square root of 5 modulus. So my answer is going to be 16 over square root of 5. We have ridiculously useful formulas to find the distance between two parallel planes, which we have improvised to use it to find the distance between a point and a plane. In fact, if you were to look at the Achevas TV theory outline, you will see on the very last page of the vectors outline, I talk about finding the distance between the point and the plane, and I'm using exactly the same formula. So we are a really very, very useful formula, just like what Claire, I remember you mentioned it the last time also. So Claire is once again declaring that this is a very, very useful formula. So we found that the distance between A to this plane is 16 square root of 15. So this shortest distance, so 16 over square root of 5. And the last part, part 5. Part 5, we are supposed to work on the shortest possible distance from M to the rectangular base A, B, C, D. And the scenario is this: there's a line L that passes through the point A, and this line L is parallel to the normal vector of the plane B, C, F, G. And the place where this line is going to be intersecting the plane B, C, F, G, it is indicated as M, and this is the point where we are supposed to find with the shortest possible distance between this point and the rectangular base A, B, C, D. So the strategy is this. Let me just redraw the diagram again. So we have point A, and just now we drew that plane. This plane is the plane that passes through B, C, F, G, and a line passes through A and it is parallel to the normal vector. So this line is going to be parallel to the normal vector of B, C, F, G. We have recorded it down here. The normal is 2, 0, 1. When in case you can remember, to get this 2, 0, 1, just now we took this vector cross this vector. So by using the right hand screw rule, we actually took this cross this, which will give us another normal vector that is perpendicular to this. Oh, my diagram is like bad. Let me draw it again. Okay, we have a vector that is parallel to BC, and we cross it with, oh no, okay, we cross it with a vector that is parallel to BG. So let me try. A vector that is parallel to BG. So we took this vector, cross this vector. So the direction that we cross is this. So if we were to use the right hand screw rule, we are going to be getting this vector, which we know that it is parallel to 201. Just now we got it as 603, but we know there will be this vector that is parallel to 201 that is pointing in this direction. So it's pointing in that direction away from A, so we know it is like that. Okay, and according to the question, this point here is M. We are supposed to find the shortest possible distance between M and the base. The base actually passes through A, right? So we are trying to find this distance here. And you know what is the difficult thing about this question? This question says that we must make use of the information that we have gotten in part 4. And the information that we have gotten in part 4 indicates to us that the distance, just let me use another color. The distance between A and M was 16 over square root of 5. So I'm going to do something which I'm not very sure whether every one of you will be able to get it, okay? But my intention is this. My intention is to find the coordinate of M. My intention is to find the coordinate of M because I know that the Z coordinate of M, with the Z coordinate of M is going to represent this distance here. The shortest possible distance from M to the plane A, B, C, D. Okay, so to find this distance, let's try to find the coordinates or the position vector of M, and then extracting out the Z coordinate of M, that will give me the shortest possible distance that the question says. And for me to do that, it is what I'm not very sure whether every one of you will be able to get it, but it's actually very, very simple. We are going to make use of unit vectors. We know there's a vector that is going in this direction, and that is 2, 0, 1. And if I were to find the unit vector of this, it is going to be 2, 0, 1 divided by its own magnitude, correct? So magnitude of 2, 0, 1 is this, which gives me 2, 0, 1 divided by square root of 2 square plus 0 square plus 1 square. It is 2 over, this is going to be 2, 0, 1 over square root of 5. Why are we looking at a unit vector? You know, one good thing about unit vector is that because this unit vector is still going to be parallel to 2, 0, 1, but its magnitude is 1. The moment when its magnitude is 1, it's very easy for me to scale this vector, right? If I were to multiply a unit vector by 3, the magnitude will become 3, but it will retain the same direction. So what I'm going to do is, I'm going to scale this into its unit vector. Then I will multiply it by 16 over square root of 5 to scale that unit vector to the same length as AM. Because by doing so, I will be able to find the vector AM. So it will be 16 over square root of 5 multiplied by the unit vector. And this gives me a 16 over square root of 5. Sorry, 16 over 5. This gives me a 16 over 5 of 2, 0, 1. So vector AM is this, and vector AM is OM minus away OA. OM minus OA, it will be 16 over 5 of 2, 0, 1. This implies that vector OM is going to be this 16 over 5 of 2, 0, 1 plus OA. OA is minus 4, minus 2, 0. So minus 4, minus 2, 0. This gives me OM, let me see. This gives me OM as, this will give me OM as 12 over 5. Then and minus 2 and a 16 over 5. And now what we have planned, if I can just extract the Z coordinate of M, that will represent the shortest possible distance from M to the base. So the Z coordinate of M is 16 over 5 here. So the shortest possible distance that the question is asking for will be this 16 over 5. Okay, so this is question number 9. Okay, let me continue with the next question. The next question is I don't know, I find it a bit unusual. Not just because of the scenario that is given, okay. I find the next question a little bit more unusual because of the way that it is asked. Question number 10. Let's take a look. Has any one of you already done question number 10? That day I saw one of my tuition students doing question number 11. For when I was trying to use the unit vector, I'm not sure what exists in your school's I'm not sure what exists in your school's notes. Okay, but I didn't use it as a formula. I use it as just something that we often use when something that we often do when we try to make use of unit vector. Like what I was saying, if I for example, if I have a vector A. If I have a vector A and if I were to take the unit vector of A, that means I'm going to take A and I'm going to chop it into, I'm going to just proportion it into this. So this will form for me a unit vector. That means for a unit vector, which is this A over modulus of A, of course we can give it a notation which is this A cap. Unit vector has a magnitude of 1, right? It has a magnitude of 1. So by using simple scaling, I know if I were to take 3, multiply by the unit vector, I'll immediately get another vector, and this vector is going to be 3 units, but it is going to retain the same direction as A cap, which is going to be the same direction as A. Well, that's how we managed to find AM just now. To find AM, what we did was we took the direction of the normal, which is going to be parallel to AM. We found its unit vector, so we immediately scale it to a vector that is 1 unit, but it is still going to be parallel to AM. Then we multiply it by the distance of AM to immediately scale it to the same length as AM, and that is how we managed to get the vector AM. And many times that's how we make use of unit vectors. Do you know when we use it? We use it, for example, the vector I. The vector I is actually a unit vector. It is 1, 0, 0. So when we try to write things that is like 5i, we can see immediately that 5i is going to be in the x direction and it has 5 units, right? Because I is actually a unit vector that is in the x direction, and multiplying I by a scalar multiple immediately help me to scale that vector to a unit of 5. So we are using unit vectors all the time, especially in the I, J, K. Okay, anyway, let me take a look at this question number 10. Question number 10. Actually, maybe I should just put this here, right? So, question number 10. We are looking at a cone, and according to this question number 10, the height of the cone is 4 over 3 of the radius of the base. So if I were to say the base is, for example, this here, let's say this is R, that means the height of the cone is going to be equal to 4 over 3 R. given that V is the volume of the cone and A is the curved surface area, we want to write down V and A in terms of R. I guess this is easy. So A part 1, V is going to be 1 over 3 pi R square H. So this is going to be equal to 1 over 3 pi R square H. H is going to be 4 over 3 R. So V is going to be equal to 4 over 9 of pi R cubed. And to find A, let me write it down here. To find A, the curved surface, A is the curved surface area. You can memorize the formula, or we can definitely just make use of what that is already given to us by the question. It is pi R L. It is going to be pi R L is this length here. So we can make use of the Pythagoras theorem, right? So sorry, maybe I should just, okay. So we have this. Okay, this is going to be L. Here is R. Here is H. So L, by making use of the Pythagoras theorem, what we have now is a square root of R square plus H square. So this is equal to pi R square root of R square plus H. H is 4 over 3R square. So this will be pi R square root of R square plus 16 over 9 of R square. And if you were to work this out, this is going to be equal to 5 over 3. 5 over 3 of pi R square. Okay, V is equal to this, A is equal to this. And hence we are supposed to find the rate of change of A with respect to V. This is not a very common phrase to see in H2 math, but you will see this quite a lot when you go to university. Once in a while, I do see this happening in H2 math. Find the rate of change of a variable with respect to another variable, and this other variable happen to be not time, and that is okay. Rate of change of A with respect to V represents represents dA dV. dA dV. It is like when they say find the rate of change of A with respect to time, it is dA dt. Find the rate of change of A with respect to V, it will be dA dV. Okay? So what I am going to do, it is not the only way that this can be done, but I will suggest that if we want to go for a simpler and more a simpler, it has become gray color. Hang on, let me change it back to black color. If we want to go for a more efficient set of solution, one way that we can make use of is implicit differentiation to be differentiating A, which is 5 over 3 pi R square. I'm going to differentiate this with respect to V. This will give me dA. This will give me dA dV, implicit differentiation. Since the question asks for dA dV, so I differentiate this with respect to V. I get this. It will be 5 over 3 pi. Differentiating R squared with respect to V, it will be 2R of dr dV. And we need a dr dV. And from here is where we can get a dr dV. By differentiating this with respect to R, this is going to be 4 over 9 of pi 3R square. So we have a 4 over 3 of pi R square. Where dV dr is 4 over 3 pi R square, which means that dr dV will be 1 over this. So I'm going to re-express this as 5 over 3 pi times 2R. Actually, we should just simplify it. Never mind. I'll just leave it as this. So, okay, let's simplify this. So it will be 10 pi R over 3. dr dV is 1 over this. So it's going to be 3 over 4 pi R square. So this pi and pi can be cancelled. 10 and 4, 3 and 3 can be cancelled. 10 and 4, it will become 5 over 2. R squared, this will become r in the denominator. Okay, so dA dV is 5 over 2 divided by r. This implies that dA dV is proportional to 1 over r. So dA dV, according to what the question wants me to show, is inversely proportional to r, hence shown. Okay, here a slightly more unusual term that we are seeing here, but for those of you who are going to be sitting for your prelim this year, please make sure that you know terms that are like this, just in case you see this happening. And of course, we can definitely also try to make use of what we have learned in our secondary school, or to make use of chain rule. So Claire, this is definitely okay. This is totally okay. And that's why I find this question a little bit strange, because when I was looking at this question, I thought this is a rate of change question, and I thought this may be a application of differentiation question. Yes, there's a little bit of differentiation, but we don't really need to substitute any values to find any rate or any maximum, minimum, or whatever. And this question actually ended just like this. So it's a very, very unusual question to me. Then and in B is not even related to the first part. So I thought this is a very, very strange question. It took me a while to get B, because of the algebraic manipulation. Let's take a look at B together. So for B over here, we are working on an equation, and this equation is given to us as xb. Okay, so x to the power of 2 over 3. Then plus y to the power of 2 over 3. This is going to be a constant. The constant is k to the power of 2 over 3, and we know k is going to be a positive number. And according to what the question says, yeah, I think the scary thing about questions that is like this is because it's so many marks. 7 marks, and I don't really know how it is being allocated. So that makes it even harder to do during the exam. I'd rather have a lot of marks, but it is very nicely broken down by the question into, like 1 mark, 2 marks, then after that 4 marks, instead of just having one question and then goodness, 7 marks. So according to what this question says, there is a tangent to this curve. And this tangent is going to be cutting the x-axis at Q and the y-axis at R. Okay, so let me do a quick sketch of the scenario. We don't really need to know exactly how the curve is going to look like. So I'm going to just assume, okay, it is for my own visualization. So we have something that is like this. The curve which is tangent, the tangent which is something that is like this, at the point P. And according to the question, at this point P, the x coordinate is x1 and the y coordinate is y1. And according to the question, this tangent is going to be cutting the x-axis at point Q and the y-axis at point R. We want to show that the length QR is independent of where P lies. So we want to find the length. We are going to try find the length QR, and I want to make sure that my ultimate evaluated result for QR is going to be independent of x1, y1. Okay, these are constants from the perspective of P. The variables are x and y. Okay, so let's try to find the equation of this tangent first, which means that the first thing that I'm going to do is I'm going to differentiate this to find an expression for dy dx. So differentiating this, I will have a 2 over 3 x to the power of minus 1 over 3 plus implicit differentiation for this, it will be 2 over 3 y to the power of 1 over 3 then dy dx. This is equal to 0. So 2 over 3 can be cancelled. That means dy dx, sorry, this is minus. Dy dx is going to be bringing this over to the other side, cancelling away the 2 over 3, bringing this over to the other side, we have a minus x to the power of minus 1 over 3 divided by y to the power of minus 1 over 3. And of course, I can rewrite this as minus of y to the power of 1 over 3 divided by x to the power of 1 over 3, or just simply negative of y over x, the whole thing to the power of 1 over 3. And our aim is to find the equation of the tangent at the point P. So at the point P, I know the x coordinate is going to be equal to x1. I know the y coordinate is going to be y1. And now we also know that dy dx, the gradient of the tangent at the point P, is going to be minus of y1 over x1 to the power of 1 over 3. This can help us then to find the equation of the tangent. So the tangent at the point P will be y minus the way the y coordinate y1 is equal to the gradient, which is minus y1 over x1 to the power of 1 over 3 of x minus the x coordinate x1. So this is the equation of the tangent. We're going to try to find the coordinates of Q, and we're going to try to find the coordinates of R. Because with the coordinates, then I will know that I will be able to find the length of QR. The length of QR. Yep. So let's say R. R, the x coordinate is 0. So we want to find the corresponding y coordinate. Letting x be equal to 0 at R. What we will be getting is y minus y1. Please take note again, y1, x1, they are constants. This is equal to minus of y1 over x1 to the power of 1 over 3 multiplied by, when x is equal to 0, minus x1. So y is going to be equal to minus minus, it will become positive. And we will have a y to the power of 1 over 3 divided by y1 to the power of 1 over 3, x1 to the power of 1 over 3 multiplied by x1 plus y1. So y is going to be equal to x1 divided by x1 to the power of 1 over 3. This is x to the 1 to the power of 2 over 3 of y1 to the power of 1 over 3 plus y1. So we know the coordinates of R. The coordinates of R will be 0 for the x coordinate, and the corresponding y coordinate will be y1 to the power of 2 over 3, x1 to the power of 2 over 3, y1 to the power of 1 over 3, then plus y1. Okay, this is the coordinates of the point R. We are definitely going to continue to find the coordinates of the point Q. So for the point Q at Q. At the point Q, I know the y coordinate is 0. So by letting y to be equal to 0, what we're going to do is to find the x coordinate. Letting y to be equal to 0, we have a 0 minus y1. This is equal to minus of y1 to the power of 1 over 3, y1 over x1 to the power of 1 over 3, then x minus x1. Multiplying this across to the other side together with the negative, this gives me a y1. Then I have a x1 to the power of 1 over 3 divided by y1 to the power of 1 over 3. This will be x minus x1, which means that x is going to be equal to this, which will be a y1 to the power of 1 over 3, x1 to the power of 1 over 3, y1 to the power of 2 over 3 plus x1. So this is the x coordinate of the point Q, which means that Q will have a coordinate of x1 to the power of 1 over 3, y1 to the power of 2 over 3, then plus x1, comma 0. Okay, so the coordinate of R I have, the coordinate of Q I also have. And the tedious thing is now we got to find the length R and the length QR. I need some space, okay, so I'm going to erase this. So let me just leave myself with the coordinate of R and the coordinate of Q. So with this, I am going to find RQ or QR. Let's just follow the notation from the question. So let me find the distance QR. So the distance QR is going to be square root of, I don't even know how long I'm going to draw this, so I'm going to draw this later, okay? So it's going to be, why not let's just make use of the Pythagoras theorem. It is this length and this length. So, so I'm going to take this length here. It is going to be x1 to the power of 1 over 3, y1 to the power of 2 over 3, plus x1 square. Where this length is the x coordinate, so we are looking at this. Okay, then plus this distance here, which is going to be taking this square. Okay, so it is going to be this x1 to the power of 2 over 3, y1 to the power of 1 over 3, plus y1 square. Okay, and now let me let me draw in this let me complete this square root. So this is where I have to very honestly say, okay, this is where it took me a while before I managed to prove that QR is independent of x1 and y1. So let me just show you how that can be done. But I don't think it is a super good example because you don't see how how I've been doing a little bit of tests here and there, to see how I can get a number that is independent of x1 and y1. So I'm just showing you the result of my exploration. When you're doing this yourself, it is okay that you are trying to do a bit of algebraic exploration also. So square root, and I'm not going to complete this horizontal line yet. I tried expanding. It took it got a little bit too tedious. So what we can do is we can factorize out x1 to the power of 1 over 3. So factorizing this out with the square, I will have this square, and I will be left with y1 to the power of 2 over 3 plus this. It will be x1 to the power of 2 over 3. And let's not forget the square. I'll do the same thing for this. I'll factorize out y1 to the power of 1 over 3. So that will be a square. Then I'll be left with a x1 to the power of 2 over 3. Then plus a y1 to the power of 2 over 3 square. Because y1 to the power of 1 over 3 times y1 to the power of 2 over 3 will give me y1. And this square root. And the reason why we are doing this is because this and this is not just that they are the same, but it is because P is a point that lies on this curve. And this curve is defined by this. So P should satisfy this, which means that x1 to the power of 2 over 3 plus y1 to the power of 2 over 3, this will be just k to the power of 2 over 3. Okay, if I were to substitute x1 and y1 into this equation, this tells me that this is going to be k to the power of 2 over 3 square. This is the same. This is going to be k to the power of 2 over 3 square. And we will have x1 to the power of 2 over 3, 1 over 3, 2. It will be 2 over 3. Then this will be y1 to the power of 2 over 3. Similarly, 1/3 and 2 times together, it is going to be this plus this square root. And we can factorize out this, which is k to the power of 2 over, let's just put it as 4 over 3. Okay, so k, so we will have k to the power of 4 over 3, and then we will have x1 to the power of 2 over 3 plus y1 to the power of 2 over 3 and square root. Then it will be square root of, this is going to be k to the power of 4 over 3. Then this will be another k to the power of 2 over 3. Okay, so this is going to be square root of k square, and this is going to be equal to k, which is independent of x1 and y1. Therefore, we have shown that PQ is independent of P. We are a very the kind of algebraic manipulation that will definitely require us to do a bit of exploration even during the exam. So I'm encouraging my class to be doing something that is like this for the last 3 weeks. So in case some of you from my tuition class is looking at this, I do encourage you to just give this a try again without looking at what I've been writing down now. We just give it a try again to see whether you can get yourself be a bit more comfortable with doing this kind of try and error during the exam. Okay, let's move on to the very last question. The last question also will require us to do a bit of try and error. This last question. This last question is actually not very difficult. It's just a question that requires us time, to do a bit of test here and there, especially B. I think A is pretty okay. A. I want to find the sum of all the integers that are between 2000 and 1000, both inclusive, that are not divisible by 7. Okay, A is independent of B. Okay, so let's just quickly take a look at A first. Okay, I want to find the sum of all the integers between 200 and 1000 that are not divisible by 7. So what I'm going to do is I'm going to just sum everything from 200 to 1000. Then I'll minus away those numbers that are divisible by 7. So the sum that we are talking about, it will be this 200 plus 201 plus 202 plus all the way until we get a 1000. So I'll take this sum and I'll minus away those that are divisible by 7. I've actually found those numbers already. The numbers that are divisible by 7, they are 203 and then plus 7. So 210, then plus 7 again, 217, all the way until the very last number that is before 1000 that is still divisible by 7 is 994. Where this is going to give me the sum that the question is asking for. And just in case you are somehow really lazy to think about the numbers that are here, you can actually press using a calculator. I don't find it actually faster, but if you are interested, you can actually do something that is like this. Let me show you. Okay, not exactly the most efficient strategy, but 200 to 1000, I think this is okay. It's just 200, 201, 202, 203, all the way until 1000. But it is this, in case you are lazy in coming up with the numbers yourself, you can consider pressing x divided by 7 into your calculator. Then you can try to generate a table. And in my table, I know that the first number must definitely be more than 200. So I press second window to trigger table setup. In table setup, I'll try to change this table start to 200. So my table starts at 200. For those of you who are doing statistics, and in case you didn't know this, please make sure that you do know this, because it is going to be very, very useful. You are not going to just keep pressing up and down on your calculator to scroll down the table in case you realize that the numbers are so big. So this is one way that you can actually make use of the function that is on your calculator table setup, right, to jump to a value that is slightly later. So we have this, and let me show you what I will be getting. Okay, so if you were to now generate the table on your calculator, you will start at 200, and basically I'm just trying to find those that are divisible by 7, which are whole numbers. So I know 203 is divisible by 7, then after that 210 is divisible by 7. If this is divisible by 7, the next number should be plus 7, plus 7, plus 7, correct? And just to show you, I think I have it. Yep, just to show you, if I were to scroll all the way until a number that is, I'll use table set to go to 1000. Then I'll scroll back a little bit. I see that 994 is the last number that is divisible by 7. The next number is going to be at 1001, okay, which is outside the range that we're considering. That's why I know these are the set of numbers. Okay, so anyway, this is I mean, this is not very necessary, but just since we have our calculator, I don't think 7 times x is going to work. All the numbers are going to be possible to be multiplied by 7. I don't think I can see the I don't think I can see it that well. Okay, if I were to use 7 times x or x times 7, I think dividing is easier for me to filter out those numbers that are divisible by 7. So here we have an AP, right? We have an AP. We have an AP with the first term as 200. And we can see what is the common difference. The common difference is plus 1, plus 1, plus 1. So common difference is 1. And how about the number of terms? The number of terms will be 1000 minus 200 plus 1. So the number of terms that we are talking about is 801 number of terms. Okay, or you can just use your observation. 201, 202, so 1 all the way until 1000. I mean 201 all the way until 1000, there will be 800 terms, then plus 1 more, 801 term. Here, we are seeing another AP. This is another AP with the first term as 203. The common difference is going to be equal to 7, since plus 7, plus 7, plus 7. And the number of terms, how do we work out the number of terms for this? Of course, you can try to use observation, but we can also do a little bit of calculation. Let me show you. We can make use of the last term that we have found. And since we know that it is an AP, so for this very last term that we have found, it is going to be A plus n minus 1 times D should be this 994, correct? So A is 203 plus n minus 1 times D. D is 7. If I were to let this be 994, I will be able to find n, and this n is 114. So I know the number of terms is 114. So the sum will be, this is sum of an AP, the total number of terms 801 divided by 2. Then the first term 200 plus the last term 1000. Then minus away this, the number of terms 114 divided by 2. The first term 203 and the last term 994. Pressing this into the calculator, this gives me a 412371. Okay, so A is fine. In fact, B, if you have had tried B without the time constraint, I think it is actually pretty possible to do something that is like B. But under exam condition, and especially with this being the last question, I think I will probably freak out a little bit. Okay, if I were to just not even do, but to just see the diagram itself, right, it's just very intimidating. But it is actually pretty okay. Let's try to take a look at it together. Okay, I'm thinking about how I should present this to you so that it is at least clear enough. I'm going to try to present this entire thing in a form of a table, and you guys try, okay, to see whether you can follow the pattern that we are going to be seeing according to what the question has mentioned. So the question says that we have this equilateral triangle, and according to the question, right, for this equilateral triangle, the sides are going to be divided into 3 equal length segments. So this side, for example, is divided into 1 segment, 2 segments, 3 segments, 3 equal segments. And for the middle segment, it's going to form an equilateral triangle. So this distance is also going to be the same as this distance. Then the middle segment is going to be removed. So we get another shape that is this, which is the same length as this, which is the same length as this, and which is the same length as this. So this, and this is repeated. So this side, for example, is continued to get this. Okay. And the first, second, third iteration comes from figure 2, figure 3, figure 4. So this will be the 0th iteration This will be considered as the first iteration, then the second iteration, and the third iteration. Okay, so first is this, okay, not this, okay? So the 0th iteration is this. And if 0 represents this area, if A0 represents this area, and that means A1 will be this area, right? This will be A1, according to what the question says. That means this tiny thing here is going to be A2, and then A3, and so on. And we are supposed to show that for the nth iteration, and n starts from here. So for the nth iteration, we are talking about here onwards. Wait, n1, n2, I mean, n is equal to 1, n is equal to 2 onwards. We are supposed to show that an is equal to 1 over 9 an minus 1, where an is the area of the new triangle that is being formed. So if I were to just take an example, let's say let's say we take this example, okay? So let's say a triangle is this, a general triangle, for example. So let's say the area of this triangle, I'm going to go for a n minus 1th iteration. So let's say this is a n minus 1 in general. I know this is going to give me another triangle, which is probably something that is like this for this side. You know, if I were to cut it into equal length, equal length, equal length, equal length. So I'm going to be getting this triangle, and I'm going to call this triangle an. So with this, and I think what I'm going to do is I'm going to call the side, the entire side, this is an equilateral triangle, so as x, which means that this is going to be 1 over 3 of x. Okay, so part 1, I'm doing part 1, sorry, I'm doing part 1 here, okay? So for the triangle an minus 1, what is the area? I mean, an is the area, okay? So what is an minus 1? I'm going to use the half AB sine C. So it'll be half times x, then sine of the angle, and that is pi over 3. So this is equal to x squared over 2 sine pi over 3. And an, the triangle an, this triangle, it will be 1 over 3 of, 1 over 2 half AB sine C. So it will be 1 over 2 of the sides. This time it is 1 over 3x and 1 over 3x, and then sine of pi over 3. So we have a 1 over 9 of x squared over 2 sine pi over 3, correct? Which means that we have this as 1 over 9 of an minus 1. Oh, actually we have already shown. So an is 1 over 9 of an minus 1 here. This is part 1. Next, part 2. Just as I was saying from the previous question number 10, right? There was that 7 marks question. I was saying that I would rather have a question that is divided into smaller parts. And I guess I'm wrong. Now I have a question that is divided into smaller parts, and each of the parts after this are so difficult to do during the exam because it requires a lot of guess, a lot of exploration on the spot during the exam. Let's see what we need to do. Okay, I want to write down the number of sides of the polygon in figure 1, figure 2, figure 3, and then deduce the number of new triangles in the rth iteration, in the nth iteration, and that number of new triangles is Tn. I'm going to show that it is equal to this. So for part 2, from part 2 onwards, just for me to express the pattern that I'm seeing, I'm going to try to draw a table, and even in the exam I'll probably produce this table as part of my solution, because it is part and parcel of how we are doing exploration on the spot during the exam also. So let's say let me draw a little table. So if I have my table and I'm going to look at the iteration, I'm going to call the iteration I, okay? So let's see what we are going to be getting. So during the 0th iteration, we are doing part 2. Okay, we are doing part 2 of the question. Hang on. I think I should try to shift this a little bit. try to shift this down a little bit. Oh no. Okay, so oops. Okay, so so I want to write down the number of sides of the polygons in figure 1, figure 2, figure 3. So during the 0th iteration, I'm going to look at the number of sides of the polygon. So during the 0th iteration, it is figure 1, and we have 3 sides, 1, 2, 3. And during the first iteration, which is this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12. And during the second iteration, it is going to be this. Of course, we can count. You know, if you were to count, you're going to be getting a 48. But at the same time, if you can actually observe together with me, each side that exists, because of the way the pattern goes, each side that exists will generate 4 new sides, right? Each side will generate 4 new sides. So if there are 3 sides, the number of new sides will be 3 times 4. This will give me 12. And similarly, for one side that is here, it will give me another 4 new sides. 1, 2, 3, 4. So for iteration number 2, which is this figure 3, it will be 12 times 4. That will be 48. I'm going to just do more than what the question says, okay? The question just says for figure 1, 2, and 3, right? Let me just do it for question number, for figure 4 also. So similarly, it will be 48 times 4, because every one side that we see here will generate into 4 other new sides. So this times 4, this gives me a 144. Okay, so this is what that is happening for the number of sides of the polygon for figure 1, figure 2, figure 3. And I want to deduce the number of new triangles. The number of new triangles. So for example, from here, I want to be able to deduce that for the first iteration, let's remember, okay, this is the first, it is not this, this is the 0th iteration. So for the first iteration, the number of triangles that we're talking about, number of new triangles, let me be more specific, number of new triangles. Number of new triangles will be this, this, and this. So there will be 3 new triangles during the first iteration. 48 times 4, is it not? 48 times 4, oh goodness, it's 192, so sorry. So I don't even know how I get a 144, so this is 192. So the number of new triangles for the first iteration is 3. Actually, if you can observe, 3 is because every side is going to give you 1 new triangle. Every side is going to give you 1 new triangle. So 3 sides here give me 3 triangles. And 12 sides here, every side will give me 1 new triangles. So 12 sides in the previous iteration will give me 12 new triangles in the next iteration. Similarly, 48 sides here will give me 48 new triangles in the new iteration, in the next iteration. Okay, so here will become this, this will become this, this will become this. Can? And what we are supposed to do is to deduce. Okay, so we are supposed to write down an explanation. Okay, so the explanation that I'm going to write down will be, from observation, every side in the current iteration will generate a new triangle in the next iteration. And therefore, I'm going to try to deduce for the nth iteration the number of new triangles here. So it's going to be times 4 times 4 times 4. If I were to just rewrite, this is going to be 3 times 4 to the power of, this is going to be 3 times 4, then after that this times 4 times 4 times 4. So this will be 3 times 4 to the power of 2 minus 1. This will be 3 times 4 to the power of 3 minus 1. What we are seeing here is a GP, correct? So times 4 times 4 times 4 all the way until n. Okay, so this is going to be 3 multiplied by 4 to the power of n minus 1. It goes all the way until n. So the first number 1 iteration, it will be 4 to the power of 0. So that's okay, let me just write. This will be 3 times of 4 to the power of 1 minus 1. Okay, so 1, it is 1 minus 1. 2, it is 2 minus 1. 3, it is 3 minus 1. So n, it is going to be n minus 1. And the question requires us to rewrite it into this form. So this is going to be equal to 3 multiplied by 4 to the power of n, 4 to the power of minus 1, which will be 3 over 4, then 4 to the power of n. And this gives us our Tn, which is what the question is asking for. Okay. So part 1, then after that part 2. Next, we want to find the total areas of the triangles that are added during the nth iteration, and that is an. With the total area of the triangles, and we are supposed to express an in terms of a0 and n. a0 and n. So an represents the total number of triangles. Let me write down maybe the area of a single new triangle. So area of a new triangle. Okay, area of a new triangle. So if this is a0, then the next triangle, according to what we have deduced here, a1. The next triangle is a1. So a1 is going to be 1 over 9 of a0. So this is going to be 1 over 9 a0. This is my first iteration, the area of one new triangle. Then a2. a2, using this again, it is going to be 1 over 9 of a1. So it will be 1 over 9 of this. That will be 1 over 9 times 1 over 9. So 1 over 9 square of a0. Similarly for a3, it will be 1 over 9 of a2. So this times another 1 over 9. I know it is going to be 1 over 9 to the power of 3 of a0. And if I were to go all the way, let me just clear this up a little bit. So this is Tn, and we know Tn here is 3 over 4, then 4 to the power of n. Okay, so this is the result that we have deduced until now, which means that for the nth iteration, we have a an. So a1, it is 1 over 9 a0. a2, it is 1 over 9 square a0. a3 is 1 over 9 cube a0. So this will be 1 over 9 n a0. And this is not even what we are trying to find. We are trying to find the total areas of all the new rectangles, all the new triangles. So we are talking about according to the question, ai. So a0, the first iteration, is just going to be a0. It is going to be by itself. As for a1, for a1, it is going to be the total area of all the triangles. There are 3 triangles, with each of them having an area of 1 over 9 of a0. So this is going to be 3 times of 1 over 9 of a0. Similarly for a2, it is going to be the number of triangles multiplied by the area of one single triangle. So the number of new triangles. So it is going to be 12 times of 1 over 9 square of a0. Similarly for this, it is going to be a3, which will be 48 of 1 over 9 to the power of 3 of a0. So an, which is what the question wants us to find, an is going to be equal to Tn, which is 3 over 4 to the power of n, multiplied by 1 over 9 to the power of n of a0. And this I can see is 3 over 4. 4 to the power of n, 1 over 9 to the power of n. I can rewrite it as 4 over 9 to the power of n of A0. Okay. So this total area of the triangles that are added, we are supposed to find AN. So this is also done. This is AN. And then we are supposed to show that the total area of the snowflake is equal to this, the total area of the snowflake, which means that we are going to be adding A0 to A1, A2, A3, all the way until AN. Okay, so for part 3 of the question, for part 4 of the question, we are supposed to find the total area. Let me write it down here. The total area will be A0, then plus A1, plus A2, plus A3, plus all the way until AN. A0 is still going to be equal to A0, but from A1 onwards, from A1 onwards, this whole chunk here follows this as a general formula. And this, if you to see it properly, this is going to be a GP. Let me write it down also. So okay, I can write it down here. So we have a 3 and 1 over 9 A0 plus 12 of 1 over 9 square A0, then plus 48 of 1 over 9 cube of A0, all the way until this, which is 3 over 4 over 9 to the power of n of A0. Okay, I'm just writing literally according to what I've written here, but I know every single one of the term actually follows this as a general formula. We can do a quick test. If this is A0, let's see. If I were to apply this general form to A1, that means this must be 1. Is this 3 over 4, then 4 over 9 to the power of 1, A0? It is. 4 can be cancelled. We have a 3 divided by 9. Then this should be 3 over 4 or 4 over 9 to the power of 2, A0, which is the same as this. Then plus this is 3 over 4, then 4 over 9 to the power of 3 of A0, all the way until this last term here is definitely still this, then 4 over 9 to the power of n of A0. So we are seeing here as a GP with the first term as this, and the common ratio is 4 over 9, 4 over 9, 4 over 9. So it is multiplying by 4 over 9 all the way. Sorry, I'm just reading your comments about this question. So what I'm going to do is I'm going to factorize out all the A0, which is very obvious because the question asks us to prove something where the A0 is being factorized out. So I have a 1 plus this is a sum of a GP. Sum of a GP with the first term as 3 over 4 over 9, which is okay, 1/3. Okay, then we will have a 1 minus. The common ratio is 4 over 9, 4 over 9, 4 over 9. So this is going to be 4 over 9 as the common ratio. The number of terms, we are going from A1 all the way until AN, so to the power of n. And this is going to be divided by 1 minus 4 over 9. So we have a A0 of 1 plus this divided by this. Let me see, this divided by this gives me a 3 over 5 of 1 minus 4 over 9 to the power of n. So we have a A0, 1 plus 3 over 5, this gives me 8 over 5. Then minus away 3 over 5 of 4 over 9 to the power of n, which then gives me this that I'm supposed to show. It's actually not too bad. Like seriously, I know some of you are like dying, just by looking at this. It's actually not too bad when you are doing it yourself, maybe. Because when you're doing it yourself, it is clearer how the patterns how the pattern look like. You are more sensitive to everything that you are writing. So when I was doing it myself, I actually find this pretty okay. It just takes a little bit more time. But now I'm also getting a little bit of stress here because I'm trying to explain to you and at the same time trying not to trying to see the pattern that I'm writing. But part 5, the last part, is actually very, very okay and easy. Part 5, we are supposed to look at this Koch snowflake. That is when we are trying to do this all the way until infinity. That is when n goes to infinity. When n goes to infinity, we have this Koch snowflake, and we are supposed to determine the number of iterations such that the area of the snowflake exceeds 99% of the Koch snowflake. So for the Koch snowflake, that is when we are talking about sum to infinity, and so the area of a Koch snowflake, this will be when n tends to infinity, so we are talking about a0 of 8/5 minus when n tends to infinity, this will become 0. So we are talking about 8/5 a0. And according to the question, we want to find the nth iteration. So we are talking about this 8/5 minus away 3/5 of 4/9 to the power of n. This must exceed 99%. So 0.99 of 8/5 a0. And we can cancel a0 on both left and right hand side because a0, which is the area of the first triangle, is a positive number. So doing so is not going to affect my inequality. I'm going to be left with this. And I'm going to bring everything over to the left hand side. So that will be 8/5 minus 3/5 of 4/9 to the power of n. Then minus 0.99 of 8/5. We are supposed to check whether this is bigger than 0. And this gives us a 0.016 minus away 3/5 of 4/9 to the power of n. This is bigger than 0. And let me see what is the answer. I'm going to press this into the calculator. I'm going to press this into the calculator, and oops, can I show you all the things that I tried to press into the calculator? I press this first. Okay, so I'm going to be solving this using the calculator. So I will press this entire expression into the y1 of my calculator, scrolling through the calculator, letting the calculator substitute values for n, which is x in this case. I'm trying to find those values that are bigger than 0. So this is when it is bigger than 0. Therefore, what is the least possible n? The least possible n, this is equal to 5. Okay. The least number of iterations. Yep. So the least possible n is equal to 5. Oh wow, actually we have finished the paper. Yes. This last question is really, whoa. Yep, I finished the last question. So anyway, for the Koch snowflake, because the question says that it is when the above step is going to go all the way until infinity. So the area of the Koch snowflake is when n tends to infinity. Okay, so when n here tends to infinity, this entire expression becomes 0. So this will give me the area of the Koch snowflake, where it is going to go all the way until infinity, where the pattern is just going to continue and continue and continue.